related soda reanalysis products. The first is called Soda 3, the second is called Rare 1, and the third is just coming out now. It's called Soda 4. The paper describing it is under submission. And so the global Soda 3 is comparable to the Ensemble. The Arctic regional reanalysis is comparable to Topaz, except it does not have biogeochemistry in it. And Soda 4 is comparable to Glorious 12. So Soda 3. So as I say, Soda 3 is going to look a lot like the members of the Ensemble. It's a global ocean sea ice reanalysis. It's built on MOM 5 architecture. So it's MOM 5.1. It's SIS1, which was the GFDL, very simple sea ice model. Does have both dynamics and thermodynamics in it. The tides are parametrized. The rivers, and I'll come back and talk about rivers a little later on, but the rivers are derived from the guide data set, and we do have restoring below 2 kilometers to avoid this whole problem of drift in the deep ocean. And the thing that distinguishes Soda 3 from many of the other quarter degree reanalyses is that we have an ensemble of these different Soda 3 reanalyses driven by different atmospheric forcings. I listed just a few on the earlier slide, but there are probably about 8 or 9 of these altogether. So most of the available atmospheric reanalyses. The data assimilation, given Soda's name, is very simple. It's still based essentially on an OI scheme. It does have flow-dependent error covariance and a few other features. So it's not a straight vanilla OI. The data sets are also conventional. Tim Boyer's World Ocean Database is the source of all the profiles. We have a satellite and in situ SST, and actually we're working with the satellite SST providers over at Reanalysis. So in fact, we've actually upgraded from the Pathfinder data sets. So SST is actually getting to be pretty good. And we do have bias correction in here as well. We're very interested in the errors that come in through surface flux. And so we actually run these Soda 3 reanalyses iteratively. So we will carry out a reanalysis, collect the analysis increments, analyze the analysis increments for the errors in surface forcing, modify surface forcing, and then rerun the reanalysis. So what are the strengths? So it's simple, so it's easy to understand what's going on. We can run for extended time periods. Bias is pretty low, but that's sort of by design. And we do have many experiments available, and we do have a permitting resolution. Of course, along with the strengths, we have some weaknesses. Just to give you an example. So this is the heat content anomaly in the upper 300 meters in the Indian Ocean. Soda 3 is in red. You'll see error bars. I guess they're not entirely evident on that picture, but there are error bars because, of course, we have this ensemble, and you can see a few of the other products on there. For example, ORS5 is on there as well. And looking at that picture, you see a feature which is really consistent wherever we look in Soda 3, which is that Soda 3 tends to look a whole lot like ORS5. That's sort of our feeling. Black there is actually EM4, and you can also see a feature which you'll see in different reanalysis, different examinations, which is that EM4 is kind of different from Soda 3, before about 2004, and then they tend to converge. So we have weaknesses as well. It's simple. We don't include altimetry. Freshwater budget is inaccurate. I'm really concerned about that. Of course, fronts and eddies are weak. It's not operational, and it's not maintained by an agency. So we have this problem. We can't actually guarantee continuity. Here's RARE 1. So this is our Arctic regional reanalysis. It's got a resolution which is between 2 and 5 kilometers, 75 levels in the vertical. This uppermost level is at half-meter depth. Cis-1 sea ice, and the other characteristics are like symmetry. And I'll just show you a few results from RARE 1. So this is the time mean distribution of the warm, salty Atlantic water layer, which is such an important aspect of the dynamics of the Arctic Ocean. This is that warm water flowing in from the Atlantic into the Arctic. And it's isolated from the sea ice by a cold, fresh halocline layer on top. And you can see thickness and temperature and salinity. And one of the most important features of the movement of this Atlantic water layer is that it enters a boundary current, which travels counterclockwise around the shelf plate of the Arctic Ocean. And that's very important because it transports a lot of this Atlantic water into the Pacific side of the Arctic Ocean. And that's one of the big differences we find between these quarter degree models and the, even this model is not really eddy resolving in the Arctic, but has higher resolution models, in that the boundary current is much more closely trapped to the coast, whereas the eddy permitting models tend to be much broader, and a lot of the Atlantic water does not actually make its way into the Pacific. It gets as far as the Lomonosov Bridge and then just cuts right across the Arctic basin. So again, it's an argument for the resolution. And then we can take a look at interannual variability. For example, this is for the Nordic seas. It's a depth versus time profile of temperature and color and salinity and contours. And for example, you can see the great salinity, one of the great salinity anomalies in the later 1990s there. So all kinds of interesting variability. This is that I mentioned that the Atlantic water layer is capped by this fresh halocline layer. So this is the distribution of the fresh halocline layer. For example, this is what I think it's vertical axis is depth, horizontal axis is time, and the colors are salinity. And so you see this fresh anomaly coming in after 2010. So again, interesting variability. And then I'll also show you the Kara Sea. Kara Sea is just to the east of the Barents Sea. So this is the variability in the Kara Sea. Colors are temperature now, vertical axis again is depth, and you see the rather dramatic warming of the Kara Sea. And that's actually, there's a lot of observational evidence to indicate that, or some observational evidence to indicate that that has been happening. However, if you take a look at these no model analyses, a data-driven analysis like EN4, you don't see any of that variability. And that's because a lot of the Russian data stopped after about year 2000. So if you want to look at the variability in something like the Kara Sea, you just cannot do it with a an analysis that does not have the full data assimilation infrastructure. And so that's another one of my
suggestions to this group is that, you know, reanalysis is so important. And SOTA 4, so SOTA 4 again is our version of GLORAS 12. You know, everything looks similar on the slide, except that the resolution is 1/10 degree. So we're a little bit coarser in the horizontal than GLORAS 12. We have somewhat higher vertical resolution, but many in the upper 500 meters, actually the vertical resolution is very similar to GLORAS 12, and most of the extra resolution is deeper in the ocean. So that's, so we were talking about analysis increments yesterday as a way of getting at bias. The pictures that you're seeing on the left are the time mean temperature analysis increments in SOTA 3 in the upper panel, and SOTA 4, this higher resolution analysis in the lower panel. And so the first thing you might see when you take a look at these time mean analysis increments is you're saying to yourself, hey, Jim, you know, you got this expensive 10th degree model, and here the analysis increments look so similar. And that's true. That is true. But mostly what you're looking at is what's happening in the tropics. And it turns out that a lot of our error in the tropics is not coming from the model at all. It's actually coming from the surface wind field. And we know that if we just crank up the winds just a little bit, I think it's the winds are slightly low, maybe misremembering that. Anyhow, you can change the strength of the winds just a little bit and you can get rid of all that increment along the equator. It's really a surface wind stress problem. Whereas if you look off the equator, you take a look, for example, at those western boundary current regions, you'll see that there's substantial improvement going from the upper panel to the lower panel. If you look closely, for example, at the Gulf Stream region, the upper panel shows the time mean analysis increments, again, vertically integrated and in units of watts per meter squared. For SOTA 3, the lower resolution model, and for SOTA 4, the higher resolution model. And you see they are better. And in fact, if you look at a section, so this is longitude versus depth, extending out from the coast of New Jersey, what you see is that the analysis increments for SOTA 3 and for many of, you know, whatever other analyses I've looked at where I've been able to get the analysis increments, you see this characteristic dipole pattern of the temperature analysis increments across the Gulf Stream. And what's going on is that the Gulf Stream front is insufficiently deep, it's not steep enough, and it's too diffuse. And what's happening in this higher resolution model, I'm sure the same thing is happening in GLORAS 12, is that you get a much sharper Gulf Stream front, which means that you get a much stronger Gulf Stream. So so you can see it, you can see all these changes in the analysis increments. And you also get better near surface stratification, stronger near surface stratification. So the upper two panels show temperature and salinity stratification in the upper 30 meters for SOTA 3 and in the lower two panels for SOTA 4. And again, if you take a look at that coast of New Jersey, you can see that this summertime stratification of temperature and salinity really changes the shelf circulation. So you get a stronger along shelf jet. That's what the contours are showing. And you get this cool water, which is running southwards along the coast of New Jersey, right along the shelf break. So we can really see the changes. And one more minute. Okay. And so the last example I have for you is the heat transport. So the impact of this move to higher resolution on global heat transport. So that should be one of our efforts, should be to firmly show that we can track the oceanic component of the global energy cycle. And so what I shown the panel on the left is northward heat transport in SOTA 3 time mean. SOTA 3 and SOTA 4. SOTA 4 is in solid, SOTA 3 is in dashed. Horizontal axis is latitude. Vertical axis is transport in units of petawatts. And you can see the Atlantic, Pacific, and Indian Ocean separated. And the big difference, there actually is a difference between SOTA 3 and SOTA 4. And the difference occurs when you get to the subtropics. It turns out that SOTA 4, and I'll bet this is true for Glorus, but I haven't checked, is that there is more northward heat transport. Why is that happening? Well, if you take a look at the picture over on the left-hand side, you see there is additional eddy, there's a contribution of eddy heat transport across the warm subtropical gyre into the cooler subpolar gyre. And so you have to add that eddy heat transport to the time mean heat transport. And so all of a sudden you can really see the impact of the additional eddy energy on the time mean circulation, things we really care about. So I'll skip over that. We have done a little bit of comparison to Glorus 12. Oh, I wanted to say, by the way, I am extremely impressed with Glorus 12. In fact, I confess to being very envious of just how good Glorus 12 is. I hate to tell you, but Glorus 12 is kind of my target. Hope you don't mind. Anyway, but what I've really compared is SOTA 4 to SOTA 3. So you can see strengths and weaknesses, and I think I have one last slide. So what do you recommend? Well, the big takeaway for me anyhow is that as we get to talking to for example, the large scale climate community like IPCC, I really want to encourage them to do a transition from these no model products, objective analysis product. Well, sorry, Tim, but I'd really like them to start looking seriously at the ocean reanalyses, which seems not to have been the case in the past. So anyhow, thank you very much. That's it. Yeah.
Here, it's open.
Okay. Yeah, anything comes up, you can just grab me.
Thank you very much, James. Please look at the Slido. Also, online participants, you would have the link to log into Slido. We have survey, we have the questions. So far, yeah, we don't have. Okay, now we have Gail to talk about the ECCO data. Thank you.
All right, thank you. There's something I need not to do.
You just need to up and down and right.
Okay. All right. Hi, everybody. My pleasure to be here. Thanks for inviting us. So I'm going to tell you a little bit about this reanalysis called ECCO and what we do in our group. There we go. So these are the guiding questions that I got from the organizers, and so my presentation tries to follow this, although somewhat loosely. So what kind of reanalysis products do we offer? I'm going to go in two parts. There's going to be what I'm going to call ECCO reanalysis proper, and then more. By proper, I mean that these are multi-decadal solutions that have been optimized using the MIT GCM adjoint. And so unlike most data simulation methods, what we do is actually fairly different. There are no state variable increments in what we do. Everything comes down to an optimization of parameters, which I'm going to list in a second. So this has advantages and drawbacks. The current version is called ECCO version 4. That's for the global ocean, the physics and the sea ice. Sorry, my slides are a bit busy, but so on the left, if you focus on that, is the first part of what I call parameter adjustments, and on the right is the second. So we adjust over a 20-year period forcing fields, the atmospheric state variables that drive an ocean model, and that those are listed in the top. So as you see, we adjust things like atmospheric temperature, specific humidity, and so on, wind stress. And the sizes on the right column are an indication of the amount of, the size of the problem. So these are 3 10⁻⁷ each, meaning we adjust biweekly forcing fields over 20 years. So it's a very large problem size. We basically do an optimization of this in one shot to all of our data sets over 20 years. What we get in the end is a fit to a bunch of different variables. The example here is showing model data misfits in terms of power spectra for sea level anomaly at the large scales. By large scale, I mean 3 degrees and above and larger. The black curve is from the RADS dataset, which is our constraint. The blue curve is from ECCO, and red is the model data misfits. So the point is, across the whole range of timescales, we have ocean reanalysis that is fairly consistent with the data, and the misfits are reduced. So a lot of this has to do with the first guess that we use for the atmospheric state, which contains a lot of this variability, and then the adjustments we do on top of that. On the right-hand side is another component to our so-called control vector, and these are parameterized physics in the ocean model. So the top map is an adjustment we make from the adjoint model to the so-called Jensen-McWilliams coefficient, which represents the mesoscale effects on the large scale. And the bottom is adjustments we make to the diapignal diffusivity. This is at the equator, and the top is a map at 300-meter depth. So the adjoint is able to extract information from the data to say we have large-scale misfits. To reduce those, we need to adjust this parameter here that way. And so this comes out of our optimization procedure as well. And this second part on the right has been crucial in helping us reduce spurious model drifts, and essentially the accumulation of biases. So unlike in classical data assimilation, we are actually able to tackle that explicitly. Here is the illustration of how we have in fact reduced those biases. ECCO version 4 is what's on the right-hand side. And then the previous generations of the product, ECCO version 2 and ECCO version 3 are on the left. These didn't have the adjustments to the parameterized physics besides the atmospheric forcing fields. And those maps show you model data misfits, I think at 300-meter depth. This is the time-in misfit to Argo and the rest of the hydrography data constraints we have. And so you see that it's been clearly reduced to ECCO version 4. So that has to do with the fact that we are now optimizing the parameterized physics, which allows us to fit the shape of the thermocline properly. So this was the jump that came from not considering that all of the uncertainties came from the atmosphere, but explicitly accounting for errors in the ocean model. Right. Here is sorry, this is busy. On the left is a description of the different releases we've had for this product, ECCO version 4. And on the right is a table of the data sets that are currently in the release 4 product. In this document that's listed at the bottom, where the collaborators are also included, that do this work, you'll see more about this table. And so everything that's listed here, taken over 20 years, that's our cost function. And we optimize to that, like I said, through one process. Our releases have originally covered a 20-year period. This was release 1 and 2 that I did myself, and then the ones after that have been produced at JPL by the folks listed at the bottom. And so the very latest we have covers 1992 to 2019. Couple addresses here. ecogroup.org is the website of the project. So that's where you'll find all of the information, data access points, and so on. And then there is an email, which mostly is operated by folks at JPL, in fact, but as an MIT address, where you can ask questions or complain if you don't understand something. All right, so this was what I say is ECCO proper. We also have a lot of other sort of model data products that are kind of listed here. And they fall roughly in two categories, what I would call tuned model solutions and things that are even more experimental than that. So tuned model solutions typically are created in our community using this approach called Green's function, which is a very low order kind of optimization. ECCO 2 is one of the products that falls in this category. A bunch of different other things like ECCO Darwin, which has a biochemistry component for carbon, and the so-called ECCO simulation, which is in fact a coupled ocean atmosphere state estimate. And then experimental model runs. I'm going to show you a few of those things. So this is in the bottom panel, this is the model emissives for ECCO 2. So like I said, these have not been fully optimized. These are solutions that are useful. One of their qualities is that these are 1/6 of a degree models. So they do have part of the mesoscale spectrum resolved. However, as you see, the model emissives in those solutions remain quite a bit larger than what we have in ECCO V4. So ECCO V4, the 1 degree model solutions with optimized parameterized physics is closer to data than an out-of-the-box kind of editing solution. So this to me suggests that in those models, you have to worry about properly resolving the transport rates with the mesoscale, which is not necessarily trivial and not something that's easily optimized. So these solutions are out there, they are useful, but sort of don't assume that there's like a full-on data simulation going on. There will be misfits. Here is sort of the more experimental side of things. So this is from a coupled simulations of the MIT GCM and the GEOS 5 atmosphere that have run for 14 months, I believe, at a 4-kilometer resolution. And this is a snapshot from a movie I created to illustrate this. And so the nice thing about these solutions is that they give us, while we cannot really do data simulation with them or optimization, they give us like an insight into the mesoscale, the submesoscale, and all of the signals that we need to sort of account for when we compare models and data. So this is something we use for OSCs and things like that. It makes for nice movies. This is another avenue of research in our group. This is a depiction of the makeup of well, I guess the series of plankton types that we resolve in our sort of high-end biology BGC model, which is called the Darwin model. And so here you see functional groups and size classes. There's 51 plankton types. Again, not something that's fully constrained by data. In fact, we don't have data to constrain these sort of things in detail. But a data product, a model data product that is still very scientifically useful. All right. So I've covered mostly the first question, and then I'm going to go through the other three a bit faster. The strength of the ECCO reanalysis, and I'm back to ECCO proper now, is a lot of it comes from the fact that we don't have data simulation increments. So it's a very different product than most ocean reanalysis. And I think that's sort of the main quality of ECCO in a sense, is it provides a different view on what we can get from model data combinations. Because there are no increments, the solution has closed budgets for momentum, salt, heat. And so that means we can fully interpret the results in terms of processes. There is no data simulation increments to sort of figure out what they are doing to us. The advantages of ECCO version 4 in particular come from the optimized parameters that we have included that allow us to reduce model drifts and bias accumulation. So we don't really have this issue that sequential data simulation schemes have with handling that. And one of the implications of that is we can reuse the results from the adjoint, these kind of optimized parameters, to do other model runs and extrapolate in a sense. Along with all of this, the solutions are an integral solutions to a set of equations. So we can actually rerun them, and you can rerun them yourself. It's actually fairly cheap. 20 years of ECCO version 4 takes about maybe 12 hours on a reasonable computer. And so that allows our users to also experiment with it, say, oh, what if the winds were different in this area of the ocean? What if somehow I doubled the amount of heat coming in? Things like that, to sort of, try to understand better the sensitivity of results. The adjoint itself is something you can run, again, to assess sensitivity of the results on the ocean state. One of the other things that I like to do with ECCO is sort of run very long timescales. And so I've taken this 20-year optimization, run that for like 1,000 years, which allows you to demonstrate that there is a clear reduction in modal drifts. Also allows us to discuss the kind of the mean state of the ocean and the overturning circulation taking thousands of years and stuff like that, using an ocean reanalysis, which is not common. And because we don't have increments, that tends to be favorable to running biochemistry and biology models on top, because you don't have these kind of issues with vertical velocities that sometimes mess you up. Weaknesses, I'm not going to read in details, but essentially it's computationally expensive to optimize those solutions. And so that has all sorts of implications. We can't really do like ensembles of those very easily, so we don't really have a good handling on uncertainty estimates. We don't really provide any really. We also have delays in data delivery, updates to the solutions that are maybe more than we would like, and more of those things. This one, I'm not even going to read. There was a question of how to use ECCO. This will be in the slide, so you can sort of read through it. And we're just going to move on. Future plans. So one of the things that I think we really need to achieve soon is a more sort of reliable reanalysis delivery process. We've had a history of making reanalysis available a bit at random times, so for our users, it's not really nice. We also, maybe the biggest query we get is, to get solutions extended toward present, and in fact also towards the past. So we are working on extensions. So I'll show you a slide on that to finish. In this kind of period of this coming 2-3 years, I guess, we want to release a couple of new prototypes. So one of them that's being worked actively now is a third of a degree without eddies, which has some advantages. I think the real goal, as far as I'm concerned, is to reach a 10th of a degree with a proper sort of eddy, mesoscale eddy spectrum in it, and to produce uncertainty estimates that actually are characterizing the uncertainties of our products, which we don't have. Beyond that, hopefully we'll do more. Last slide. This is something that is going to become available in the coming weeks, and that I've been working on. It's an extension, like I said, to closer to present and further in the past. So the plots illustrate model data misfits, and on the right is kind of what I did. So this is based on the release 5 of ECCO version 4, which uses the Mora 2 reanalysis for atmospheric forcing. It's been optimized, as I've described before. So what I did is I took this and I computed the monthly climatology of the adjustments we get to those forcing fields. And then you can reapply that to the Mora 2 reanalysis over a longer time period. So I did that from 1980 to 2023. That does lead to slightly less of a good fit to the data, but these pictures are meant to illustrate that nevertheless, it's a fairly useful product. So here on the left, you have the comparison between SST in this ECCO version 4 extension 1 solution compared to the NOAA OI SST product. These are anomalies from the climatological seasonal cycle. And so broadly speaking, it's a pretty good fit. There are a couple of issues that I want to work out before making this available, especially in the kind of solid notion in the beginning of the run. But I think it's a useful set of solutions that is at least complementary to the solutions we have now. And that will become a first guess for another round of optimization, which will take a bit longer, but I'm hoping to get that released next year, a fully optimized solution for this time period. And on the bottom right is it's kind of a bar plot of the so-called cost function. I'm not going to go in much detail, but basically red is kind of this sort of approach of extending the solution. Green is kind of the fully optimized target. So it's slightly less of a close fit, but this is still better than something like ECCO 2 that I was showing before, which itself is useful. So I think it's a useful set of solutions that will be complementary to what we already have. And hopefully we will have fully optimized versions of this soon as well. If you're interested in this kind of solutions, please email me. And I think I'll leave it to this and take questions if there are any. Thank you.
Thank you, Gael, for your talk. So my question is related. Do you have any thought on including wave-coupled process, ocean wave-coupled process in your ECCO? Or?
I guess there are two levels at which we can think of doing that. One is in our forward model runs, and I think we really should do that. Some of the presentations we saw yesterday about, I guess, the pathways of larvae suggest that, or I guess it was turtles, suggest that we do need to account for that. Whether we want to do this within the optimization is a different ballgame. It makes everything more expensive. And it's not obvious to me that, it's an active component in a 1-degree model solution that we really need to have. Similarly, we have experiments where we included like pressure load. It's a bit, we can argue about whether that's really useful. And then we have a kind of our high resolution models. And I think in that context, I think that's where it's going to be interesting to really couple it. Does that make sense? Yeah.
Hi, Gael. Thank you for your presentation. I had two questions. The first concerned the fact that you have this assimilation of Aquarius for sea surface salinity during few years, and you do not assimilate smolts in between. So is Aquarius impacting enough your simulation to constrain the full simulation, or did you measure the impact of Aquarius on the water budget?
So very good question, but I'm not sure I have a very good answer to it. In a way that this is part of the work that's been done by my colleagues at JPL. So I would really need to refer you to them to answer it properly. I think because we propagate, backwards in time, the data that's at the end can still improve the solutions overall to the extent that, we cannot fit the end result without having something coherent before. So that's the general philosophy that allows us to, benefit from Argo also towards the end of the period over the beginning. But the degree to which we have validated the usefulness of Aquarius in the optimization, I am not sure myself.
Hi, Gael. Thank you also for your presentation. And it's good to have this diversity in terms of reanalysis philosophy, let's say. And I have a question regarding the parameter optimization. So you've shown, for instance, the optimization of the diapinal diffusivity. And I was wondering how confident you are with this parameter optimization. Like, does it compare favorably with maps generated from observation, for instance, Waterhouse, Ketlin-Whelan, or from parameterizations themselves?
Yeah, so to some degree, I would, yeah, but it's really noisy. They're cleaning the streets outside for those online. So the comparison that I've done were, generally speaking, I think, favorable. But there is a couple of caveats. One of them is, in our procedure, we are not trying to map out exhaustively those components. Specifically, if the ocean state in some place is insensitive to vertical diffusion or the level of it, or the level of mesoscalidi activity, transport rates, then the adjoint will just not adjust those. So they will stay to their background value. Does that make sense?
I'm sorry, I just couldn't hear. I will talk
Yeah.
during the coffee break.
Okay. Maybe this will work better. So I was trying to say, our estimation process means that the model data misfits need to be sensitive to the parameters we talk about for it to get adjusted. If that's not the case, meaning the rate of the GM coefficient or the depth diffusivity does really little to impact the hydrography and the state of the ocean in a particular region, we will conserve the value of the first guess, right? So in that case, you don't really want to take it at face value. The only place that you really want to try and interpret those results that we get is where they've been adjusted. And so when I've done that in the past, a lot of it made sense. It's more patchy than probably a detailed map would be in reality. And I guess the other caveat of those comparisons is there is a lot of assumptions made when you try to back out with this method and others, these rates of transports from data, right? So I think it's a work in progress. I think we can consolidate the process to maybe get to a point where we'll claim that our adjoint results for those parameters is like the best map you might have, but that's not the case yet. All right, thank you so much.
Thank you, Gail. We already see two reanalysis. Now we go to Japan. GMA reanalysis, please.
Yes. Yeah, I'm Yosuke Fuji. Thank you for you. Yeah, thank you, Chairman. Yeah, I'm Yosuke Fuji from Japan Meteorological Agency, Meteorological Research Institute, or GMA MRI. And I'm deeply honored to be invited here and have a presentation on the ocean analysis in GMA. And yeah, today I would like to highlight on the impact of 4D bar compared with 3D bar. And I realized the author is not updated, co-author is not updated. So I would like to add Norishi Sausui and also Dr. Nariaki Hirose. And anyway, so I would like to start from the introduction. I will give you an outline of 4D bar ocean analysis system in GMA. You know, we have two ocean analysis systems. One is the global system for initializing the coupled atmosphere ocean predictions for sub-seasonal to seasonal forecasts. Sorry. And you know, the name of the system is MoveMRI.com D3, and the system is composed of two models, G3L, analysis model G3A, and also downscaling model G3F. And you know, G3A has 1 times 0.3 to 0.5 degree resolution. And we will, the 4D bar optimization is performed with this G3A analysis model. And the analysis result is downscaling into G3F. It's a quarter degree model. And the downscaling is performed through IAU or replaying. And also the other model is the regional model named MoveMRI.com NP or JPN. And it's for monitoring and prediction of the ocean state around Japan, including the cross shore, wear shore, etc. And it's composed of two models, North Pacific model and Japan area model. non-specific model has a resolution of 10 kilometers, and the adjoint 4D bar optimization is done by this non-specific model. And the analysis result is downscaling to Japan area model with 2 kilometer resolution. So, and this slide shows the procedure of downscaling or replaying. Temperature and sanity field of the downscaling model are constrained to the 4D bar results of the analysis model through incremental analysis update or IAU. And first, a preliminary prediction run of the downscaling model is performed. And the 5-day average TS prediction field are calculated like this. And the prediction field are converted to the grid of the analysis model, and increments are calculated by subtracting the prediction field from the 4D bar result of the analysis model. And the increments are converted back to the grid of the downscaling model and added gradually to the DS field in the analysis run so as to suppress the shock. And, we use 4D bar, but, it's different from the ocean estimation like ECCO. So we have analysis increments of state variables, and we have only short data estimation window. It's 10 days, and model fields are modified by gradually adding temperature and salinity increment for first 5 days by IAU, and the temperature and salinity increment are optimized so as to fit the model trajectory to observations through the iterative calculation of the forward and adjoint models. And the observation window is shifted 5 days after IAU window and overlapping with the IAU window in the next analysis cycle. And, we regarded the trajectory connecting model feeds in the second half of the assimilation window in each analysis as the real-time analysis field. So this one and this one. So, and the system performs 3D bar before the 4D bar analysis, and the result of 3D bar is used as the first guess of the 4D bar. Pre-3D bar is performed in order to reduce the computational burden and also in order to guarantee the accuracy similar to 3D bar, even if the number of the iteration is sufficient. And this slide shows how the SSD error in assimilation data is reduced. So first we have, first guess field, and maybe although the error is rather small in most areas, relatively large error can be seen at the north of New Zealand. Sorry, it's difficult. Okay, so here and here. And but the error is reduced after the pre-3D bar, and the error will be further reduced after 4D bar optimization. And we have the downscaling, first guess of the downscaling model. And in order, we reflect the 4D bar result to the downscaling model, and the error will be reduced. And this one. And next, I'll talk about the advantage of 4D bar in the eddy dissolving regional system. This figure shows the compare the increment of 3D bar and 4D bar, and the increment are elliptically distributed in 3D bar like this, but are spread out along the flow in the 4D bar. Thus, 4D bar can generate flow-dependent increments like this, and this flow-dependent nature of 4D bar improves the mesoscale representation of the analysis field. For example, this figure shows the streamline of 4D bar and 3D bar together with the ADC observations and also the observation positions. The streamline in 4D bar are in good agreement with the ADC observations. indicating that 4D bar reproduces the detailed shape of the eddy even though the observations are not sufficient dense. And this figure shows the snapshot of this date. And here the closure have the intrusion here, and this one motor intrusion is not represented in the 3D bar result like this, but in 4D bar the intrusion is successfully represented. So this improvement, and this improvement is likely caused by the flow-dependent nature of the 4D bar. And the representation of sea surface height is much improved with 4D bar. This figure compares the anomaly correlation coefficient of SSH with abyssal objective analysis. The correlation, 4D bar improves the correlation ACC much better than 3D bar like this. And this is the time series of sea level at Hachijojima Island here. And a high frequency component is much improved with 4D bar like this. And also this figure compares the power spectra of sea level at Hachijojima. And compared with 3D bar, the power spectra of the sea level at Hachijojima is increased and made closer to the observations in 4D bar. And this figure shows the impact of algal float from the OSE observing system evaluation. And this figure shows the correlation of temperature and salinity time series at each grid point between the control line and the OSE line in which algal data are withheld. And a smaller value means that the assimilating algal has a large impact. And in the closure extension area, in the circle, withholding algal data in the 4D bar does not affect the TS field compared with 3D bar. And this means that in the 4D bar, the temperature and salinity fields are well reproduced by assimilating sea surface observation mainly, without assimilating algal data. So sea surface observations are effectively used to reproduce subsurface temperature and salinity field around closure extension in 4D bar. And this figure shows the example of the prediction, closure large meander prediction. And this is the snapshot of same day, but the initial date is different. But this is the answer. So the prediction from 3D bar tend to overestimate development of the meander and also eastward advection of the meander. But prediction from 4D bar adequately represents the large meander like this. So better subseasonal submesoscale feature and better physical balance in 4D bar improve the prediction. And next, I'll talk about the global system. And it is often difficult to prepare independent data for validation of data estimation results. So actually, prediction fields initialized by DA are often compared with observation data, which have not been assimilated yet. But the observation may not be truly independent of the prediction field because their representativeness error may be correlated with those of the past observation. So in this study, we withheld the data from algal float whose last digit of the WMO number is 8 or 9 and used them for validation. And this is the distribution of the algal float with WMO number is 8 or 9 and 20% of random profiles. The independent algal float is distributing like globally like this. So and in our system, the analysis of a same period is estimated twice like this. So we have real-time analysis and also delayed mode analysis. So, and this figure compares the impact of the color is, I think, it's anyway. So I show the difference of root mean square difference against the independent algo beta, algo between delayed and real-time analysis field. And, the color is not good, but yeah, basically, the real-time analysis are further improved by assimilating observation in the next 5 days in the delayed analysis, especially for 10-meter temperature. And, but, SST is not so improved because sufficient SST observation data have already constrained the real-time analysis. And yeah, very actually we have data, but not data missing. But I think why I don't know why. But anyway, in 100-meter temperature is improved. So and 4D bar has so capacity. 4D bar has a capacity of improving the analysis field using future observations. Yeah, very, yeah, shallow color. I cannot see the shallow color. Sorry. Anyway, yeah, this figure shows the comparison of the bias from, sorry. Yeah, bias from the objective SST analysis. And also, as so here I would like to show the impact of reducing data misfit effectively in 4D bar. In the 3D bar, relatively large bias are found, particularly in the tropical region. Yeah, we cannot see, but we have large, relatively large area around here. But 4D bar effectively reduce the SST bias from the estimated SST data compared with 3D bar. Yeah, no bias. Yeah, and also, we compare the difference of RMS reads from assimilated algo data between 4D bar and 3D bar. And, RMS reads from assimilated algo data are also generally reduced by 4D bar like this. Thus, 4D bar more effectively reduce the data misfits. But it does not necessarily mean that the actually analysis error is reduced with 4D bar. And this figure compares the root mean square difference between the analysis and independent algo data. So it's kind of true actual error. And the impact of 4D bar. And 4D bar reduces SST bias more effectively than 3D bar like this. But the impact of 4D bar on 100-meter temperature bias and root mean square difference on SST and 100-meter temperature seem to be neutral. And probably because the model does not sufficiently represent the real physics due to the low resolution. But 4D bar performed better than 3D bar. Sorry, better than 3D bar in the equatorial Pacific and the closure extension area. And actually, 4D bar reproduces variation of the equatorial Pacific thermocline much better than 3D bar. And thus, 4D bar tend to reproduce large variation better than 3D bar. And this figure shows the impact on the 4D bar forecasts. 4D bar predicts SST variation better in the region where TIW are active and the western boundary current region like this. And the impact can be seen even in the forecast more than a month ahead. So it may be due to better physical balance in the 4D bar. And finally, I would like to talk about the future plan. Sorry, we are now developing the direct assimilation of level 2 or level 3 SST, satellite SST data using weak constraint procedure. And also, we are now doing the regional analysis named FORA JPN60. So please see the poster of JMA. And also, we are now performing the OSE for the UNDK project, SYNOPS. And in the future, we would like to assimilate coastal data to the downscale 2-kilometer resolution model using 3D bar. And also, we want to develop quarter-degree resolution global ocean 4D bar system with 1-day observation window. This figure compares the impact of the 4D bar with the 1-day observation window. For 1-day observation window, impact of 4D bar is large. So the performance of 4D bar becomes worse when the observation window is shortened, but 3D bar is also worse, but the degrade in 4D bar is smaller than 3D bar. The 4D bar impact is enhanced for the shorter observation window. So we consider using one-day observation window is feasible with 4D bar. And finally, I would like to introduce the CNOVS. CNOVS is UN Ocean Decade Project led by CNOVS is UN Ocean Decade Project led by Ocean Predict Observing System Evaluation Task Team. And CNOVS will seek the way to extract maximum benefits from the combination among various observation platforms, typically between satellite and in-situ observation data in ocean predictions. And CNOVS plan to implement OSEs or OSSEs using various ocean prediction systems with a common setting. And these are the OSEs observation data setting. And more than 10 ocean systems will participate in this collaborative activity. So if you are interested in, please contact me. That's it. Thank you for your attention.
Thanks. My question is about my question is about your the impact of 4D VAR compared to 3D VAR on the extended range. So you show something on SST even at 2 months of forecast lead. But for instance, on precipitation, other atmospheric verification, you can see the impact, or it's a bit more hidden by other factors.
Yeah, I examined the impact on the ENSO, and the ENSO prediction is a bit improved for 2 or 3 months prediction. I'm not sure about the precipitation or some other atmospheric variables. But we have a stronger frontal structure for cross shore, so it may be improved the precipitation. But it's not easy to find the impact on atmosphere, I think.
Okay, no other questions? Thank you very much, Yusuke. Yeah, thank you. Now we have Romain to talk about a Copernicus Marine Service reanalysis. Please.
Okay. Thank you. Good morning. I'm going to talk about the global ocean reanalysis in Copernicus Marine Service. Marie yesterday shown this slide, which describes the different products we have in the Copernicus Marine. And here, I want to stress your attention that I'm going talking about ocean model data over several decades at the global scale. And to do this job, we are several institutions which are involved. Some of them are mainly producer in red, like ECMWF, Meteo France, MCC, and Mercator Ocean. And 2 others are more focusing on the validation and process 2D, BGOS, and CNR. Here again, Marie showed this slide yesterday. I think this is to describe the different period we have depending on the observation system, because there is a strong link in reanalysis with the observation system. And here we have divided in a 3 streams, one covering the Argo period, one the altimetry data, and one long multi-year period. With just in situ in the past. And for the moment in Copernicus Marine, we are just working. We have just some products on the stream 2, focusing on the mesoscale fissure and interannual variability. I mean, this is covering the altimetric period. And we're working on the stream 3, but it's not yet on the catalog. Here, this is just a snapshot of the web page you have when you enter on the Copernicus Marine, and you can select, if you select here ocean product and you put a longer time series, ocean, model, etc. Basically, you have 3 icons. And these 3 icons correspond, in fact, on 2 products. One is a global 112 degree that have been mentioned during this day. And the 2 other one, this is a global quarter degree. Just we have 2 because we have 2 resolution for the distribution. But in fact, this is the same product behind. I will concentrate my talk on these 2 products. Last thing, the question is this product useful and downloaded? The answer is yes. Here I show you a statistic on the Copernicus Marine portal on the download of different products. The first one you see in blue at the top, this is the ocean forecast. And the second one, this is a global 112 reanalysis. So this is one of most downloaded products that we have. And the multi-ensemble product based at the quarter degree has up to 800 downloads this year. It's a little bit less than the year before because it's an older product. So this download corresponds more to some upgrade for the new year we have produced. And in terms of repartition, we cover download where the downloads are done. We cover basically all the world, and our main user are university, then public sectors and business. This is just a schematic of our user. Okay, now I go briefly through the different system. The global 112 degrees that I've already was presented by some study yesterday. The reference paper is Lelouch et al. 2021. This is a 112 degree grid. It means 9 kilometers at the equator and close to 3 kilometers close to the pole. And with a 50 vertical mode, forced by error interim, then error 5 at the end. And the SLA, SST, and TS profile as assimilated thanks to 6 method. The idea here is focusing on the mesoscale activity, and this is just a snapshot to illustrate the different features that you can have in this product. Also, I want to mention Jean-Michel ran this first analysis, and he has run also a 112 degree without data assimilation and 1/4 degree exactly the same with data assimilation. And thanks to that, we can have an estimate of the benefits of resolution or data assimilation. Yeah, it's a pointer, sorry. Okay, Marie shows this slide again. This is integrated quantities. This is the first validation we do. And here you have the 112 degree in red. This is comparison of temperature and salinity, temperature at the top, salinity at the bottom on the left. And you can see that thanks to data assimilation, the statistic compared to the data assimilated are very good and better than a free run in orange and better also than climatology, particularly for temperature. In terms of sea level anomaly, we have a small bias and which is increasing at the end of the time series. So that's why we know this reanalysis become a little bit warmer. We have a small warm drift in this product. And this is due to this tuning. And in terms, but nevertheless, in terms of a root mean square, we are almost stable, close to 5 centimeters, sorry, compared to the sea level anomaly. In terms of dynamic, here I'm talking about the 100 degrees. So this is not completely a depermitting model, but a rich AD model that we call now. So we have the capability to have AD. So first thing we want to check is energy and how is the repartition. Here I show you the AD kinetic, geostrophic AD kinetic energy at the top left of GLORIS 12 over, I don't remember, 2010, 2016, I think. And the other plot are GLORIS 12 minus different product. First is the Aviso at the top, and at the bottom, this is a free run at left, and the global quarter degree run, the twin one, at the right. And what you see is major current, Western boundary current, etc., are well in place thanks to the data assimilation. But compared to other products, GLORIS 12 show more energy. This is expected. This energy is expected because there is a resolution, but also compared to Aviso, the horizontal resolution, but also compared to Aviso, sorry, there is a temporal one. So this is expected. We're happy. We have what we want. And if we check based on the SST power fraction, we can perform a ratio between total power spectrum of the band of 20 km to 1000 and just select the power spectrum inside the mesoscale band. And if we make the ratio, we see how many we have increased and the importance of the mesoscale band compared to the total one. And here you show this ratio for the global quarter degree and global 112 degree. And clearly there is an increase in this mesoscale band, and particularly at mid-latitude, because this is the place where this model is able to represent Hades. Okay, and here this is just some example. Yesterday we showed some study, and this is another ones in the literature, just to say that now people use it and may perform some study with it. For example, Camilla Artana et al. In the Zapiola region, compared to in situ mooring, which is assimilated, I think, regarding the very good result. If you compare the profile and GLORIS 12. But thanks to that, she is able to validate this region and to propose some schematic figure of the circulation in this region. She also do the same kind of job at the Drake Passage, for example. And if we go on the north, just published this year, Shafik et al. Show a very good agreement compared to ADCP measurement and the mean GLORIS 12 circulation. And thanks to that, they are able to have an estimation of the transport on Faroe Shetland channel, and they make the link with the sea level anomaly. So it means this channel is mainly controlled by sea level anomaly, and thanks to data assimilation, we have a pretty good representation of the variation. Okay, now I switch to other product, which is a global quarter degree. We call the Ensemble quarter degree product. This product is constructed for the moment based on 4 reanalyses at the quarter degree. All of these reanalyses are based on Nemo quarter degree with 75 vertical level. So it means 50% more than the GLORIS 12. In common, there is the atmospheric forcing, the time coverage, and all assimilated sea level anomaly, but all other features are different in terms of model parameterization, in terms also of sea ice model, in terms of data assimilation method and assimilated data. There is a different, there is different poster. Come back, yeah. There is different poster from Andrea Storto, Eric de Boissesson, Richard Henshaw, and myself, and you can have interaction and discuss with these people which describe this product and the product on what they are working on. Okay, we have these 4 products, and the idea we had some years ago, 2 or 3 years ago, is try to construct a framework to validate these different products. And we are targeting some topics to do that. And for example, here I show the 3 topics we have. The first one is the AD activity. This is done by our colleague of CNR. And the idea is intercompare the different products on the capability to represent mesoscale activity and what they are done. And here I show you just an example of the AD kinetic energy deduced from the different model. And there are, you see, of course, all the major current are well in place, but some of them are more energetic, for example. And they apply a AD detection method and compare the AD number during with these 4 products at the 1/4 degree. Main conclusion are ADs with a lifetime greater than 16 weeks, I mean the major AD, there is a very good agreement in terms of number of AD. After, when you go with a smaller AD or AD with a shorter lifetime, there is more the differences, and mainly due to the data simulation of model parameterization, and we should try to understand that. And also, that just compute exactly the same thing, but with the glory, so 1/12 degree to compare 1/12 and 1/4 degree. So here you should compare dash line and solid line for the red one, for the blue one, etc. The blue one, it is smaller than 20 kilometer, 10 kilometer. After this is a band, I don't remember, but it's a 2050, if I remember well, or something like that. And when you reach the green line, this is the biggest AD. If you compare the dash for each color and the solid line, you see that for the big AD, you have basically no difference between 1/4 and 1/12 degree in terms of number. But when you check the smallest one, you see the M factor of the resolution at mid-latitude with the dash line is always greater than the solid line. So this is to highlight the capability of Garric, for example, to create some ADs. Another work that we want, topic we want to address, this is the transport in the different analysis. And here, this is our colleague of BGS, who are working on that. They develop tools to compute a transport offline, and it works pretty well. And they are focusing on 2 regions, the Indonesian flow and the Arctic Ocean. And here, just to highlight this, I show some results on the Arctic Ocean. Okay, on the Arctic Ocean, where they compare the volume flow anomaly and also, for example, the total heat flow at the Greenland-Scotland region between different reanalysis product and also some observation with some uncertainty of observation. And they discuss that, and there is a very nice paper in the Ocean State Report by Michael Myers this year, just published. And here I encourage you to discuss with Susanna, which is she's here, and she will be happy to present his work. And last topic that we focus on, this is a trend, because this is something very important for analysis product. And here, this is our colleague of CNR, again, who are in charge of this part, and they are studying the trend. Here I show you just, for example, the steric trend for the 4/4 reanalysis product at the top and at the bottom. This is 2 objective analysis, okay? So all the trend are red as expected because there is an increase of steric. So we know all that. And they are also compare the different evolution of all the member and the mean, the mean of the member compared to the in dash line here. This is the different objective analysis. What we can say is there is 2 periods here, clearly before and after Argo period, where the spread reduce a lot after thanks to the Argo the network, because the models are more constrained. And that's it. And you can discuss with Andrea in charge of this work. So For this part, what next? For the moment, we continue to work on the GLORIS 12, and we will be extend as close as possible for the real time, because this is a user request. And also, as we should extend the Ensemble product, but we can't deliver for the moment the UCMIP product due to Brexit. We have reprocessed all the time series for the moment with only 3 members to have something more homogeneous, and we will distribute for the next year this product. And we are working on the new global 112-degree reanalysis, hopefully distributed in 2025, and also on the new Ensemble grep, and come back on that because it's based on new member. I mean, our reanalysis will be new for this grep. Just to highlight the work of our colleagues. Here, this is what is done in ORS 6. It's based on NEMO. All of this new analysis will be run with ERA 5, forced by ERA 5, sorry. And there are different features on that are working. And just to highlight one of them, here I work on the new boundary condition term and revisiting nudging. And thanks to that, they fix a problem they have. For example, some transport here. This is the old one in red. This is a transport at the Florida Strait compared to the cable measurement in black. And with a new development, there are pretty good solutions. So there is many other things, and Eric will present it in this poster. Here, this is for the CMCC. Here again, always equator degree 75 vertical level. I forget mention, or we will switch to a CIs cube model. It means a multi-category model for the CIs. And they work also on different aspects on their analysis. And just highlight two here, they work on the spatial unbiased of SLA. So thanks to that, they are gain 1 centimeter in terms of root mean square error, and also a bivariate approach on the CI's concentration and CI's thickness. And thanks to that, it avoids that fresh water and the Arctic Ocean, and they fix that. So there is also some other aspect, or basically the flux correction, etc. And Andrea will present this in this poster, and you can discuss with him. And concerning the Mercator side, we are co-developing exactly now the same quarter and 12 degree. So it means that the future GLORIS 112 degree will switch to 75 vertical levels. This is one objective, and to merge all the development because we have too many differences. We are also forced by RA5, and we are working on a new mainly on the data assimilation side. And just I mentioned here, we have work on the mass, because we are in Boussinesq approximation. So, we are not able to represent the global steric effect in our analysis. So we are trying to close the budget. Evaporation means precipitation and runoff, and force to what we want. This is a mass, and the steric is just a diagnosis. And the idea behind is to having the right trend, because we have some issue in the first GLORIS time series. And here I compare to some Aviso data, the different part of GLORIS. This is ongoing work. So main conclusion, the global analysis, we can say it's highly product on the Copernicus Marine. And I think this analysis is validate and mature enough for study, and particularly after 2005, because it can be useful for ocean state reporting now. It means that we have 15 years more or less time series, and it's very interesting. We have tried to develop also collaboration with our colleagues to have a framework for validation, to interchange some code, some etc. And I think it's a very, very interesting, a very nice collaboration. And in terms of prospect, I already say we are working on the new product on 120-degree reprocess and ensemble basis with only 3 members for the moment. And also we are thinking producing more longest time series, but there's a problem of homogeneity because when the sea level arrived in 1993, we should deal with it. And also we want to intensify some collaboration with colleagues with BGC particularly to have a good exchange in terms of variable, etc. And last but not the least, we think also with a collaboration with other team, particularly for something like new international or IP comparison or something like that, because we know that we learn a lot thanks to this approach. And that's all for me, I think.
Any questions?
Yeah, very nice presentation. If I can ask on something you didn't show, did you look at the sort of the time mean global ocean heat transport in between the 12th of a degree and the 4th of a degree? How big of a difference does that make?
Yeah, this is in the Jean-Michel paper. There is no many difference in the quarter and the 12 degree in the heat transport. And I think it's mainly due to both have data assimilation of sea level anomalies. So it means the mean transport are very close. So if you integrate over several years, for example, you recover the mean transport in terms of salt and etc. So the difference is not very huge between these two products.
Okay, thank you.
If
And here.
And
I think this is one difference with the soda.
actually, I think that's really great. We don't assimilate sea level, so maybe it has something to do with that we're not constraining.
And you plot your two curve will be very close because
Very
if you look at a large time scale. After, if you look at, for example, difference at monthly time scale, you will see some eddy center.
No, I'm interested in the timing, getting the eddy contribution in there. But actually, I just had a comment, which is I really like the idea of organizing more of these intercomparisons because I think we can learn so much, because we have these different approaches and different kind of ways of analyzing the data. So I'd like to support that.
Agree.
Maybe we see the question online later. Thank you, Romain.
Yes. So yes, there is a question on Slido and for Gael also. So you can connect on Slido and ask.
Yeah.
We have some question for you.
Yes, you can answer yourself if you want.
Yeah. Thank you, Romain. Maybe after the presentation of Ali, we'll go back to the online question. Now we go to the regional reanalysis of the Copernicus. Please, Ali.
All right. Good morning, everybody. I'm happy to deliver the message from our regional reanalysis experts today. They provided me kindly 3 slides per MFC, so I will try to do my best to deliver the messages correctly. All right. I will also try to give some, let's say, quick answers to the user requests from yesterday that we discussed. If you go to the marine data store of Copernicus Marine, you'll see these products for the regional physics reanalyses, which deliver temperature, salinity, currents, sea level, mixed layer depth, and in the white ocean, sea ice as the physical variables. And we have 6 marine forecasting centers who are producing the reanalyses, the Arctic, Baltic, Black Sea, and we have Iberian, Biscay, Irish Ocean, Mediterranean Sea, and the Northwestern Shelf. And these reanalyses provide data from hourly to yearly to multi-yearly time scales. And the ones at the bottom here are actually providing also hourly data for the 2D variables like the sea surface height and the sea surface temperature. And they also provide some monthly mean or the yearly mean products to ready for use for the users. And some general characteristics of our regional multi-year physics reanalysis systems are, most of them are based on the NEMO 3.6 or 4.0 version. We have Arctic, in the Arctic, we have the HICOM model, and they have the Kalman filter variants or the variational 3D-VAR variants, FCATs, or 3D-VAR, which are assimilating temperature, salinity, as well as the sea level anomaly, sea surface temperature, and ice. This is the general picture. Not all of them doing this, but we have systems assimilating these variables. And the resolution is varying from 2 kilometers to 12 kilometers. And in the vertical, from 1 meter resolution, possibly at the surface, to 500 meters at the bottom. And all of them are using the ERA 5 as the atmospheric forcing, and there are different resources for the rivers that are used by our experts in their reanalysis. I will scroll down alphabetically all the contributions from the experts, starting from the Arctic. In the Arctic, as I said, we have the HICOM model, version 2.2, coupled with the size version 3, and the resolution changes from 12 to 16 kilometers in the horizontal. And this is recently upgraded from 2.2.12 to 2.2.37, and the vertical resolution is increased from 28 to 50 Z isopicnic levels. This helped to improve the vertical representation of the profile, vertical representation against the Argo and the ice tethered profilers. And the river fluxes around Greenland include glacial mass loss. From the data assimilation side, the Arctic system has the deterministic Ensemble Kalman filter with 100 members, with 7 days of cycle, and assimilating sea surface temperature, sea level anomaly, and in situ, as well as the ice variables, which Gilles, I think, will tell more about this later. And the lateral boundary conditions in the Arctic reanalysis is still the climatology. And as I said, forced with the ERA 5. This has been done recently from ERA 5, ERA interim to ERA 5, this passage from 1991. And the products that are used for the data assimilation include also the sea surface temperature and sea ice thickness. This product has strong skill to represent the Arctic sea level rise, and the sea ice age are quite accurate in the Arctic reanalysis. And our experts suggest also to use this product to study the marine heat waves. And they suggest that there may be some discontinuity due to the inputs range in time. And there are very few profiles to constrain the sea ice, and 2 thin sea ice before 2010, and 2 saline surface waters in the Arctic. These are the things that should be considered while using the Arctic reanalysis. And for the future, there are foreseen new upgrades for Topaz 5. The high conversion will be upgraded, and the size will be 5.1 with 50 hybrid layers. Major challenges are the computational cost or to run this reanalysis, of course, and it takes 2 years only to produce this reanalysis. So it's foreseen, if the system is frozen in 2025, it's foreseen that in November 2026, the reanalysis will be ready. And there are boundary condition requirements from global reanalysis starting from 91. And the rivers will be provided from GLOFAS or A-HYPE, E-HYPE, and plus Greenland sea ice, land ice. And there will be improved ensemble generation. There are issues with the sea ice thickness and the sea surface salinity, which are going to be hopefully improved. And the issues that will be tackled also later on will be the assimilation of the SWOT and the tidal component will be included later also in the reanalysis system. And I already mentioned that in the Arctic Arctic reanalysis, there are different strengths and the weaknesses that you can look on, and also for the discussion later. Now I move on to the Baltic. We have a NEMO 4.0 in the Baltic with a 1 nautical mile of resolution with 56 vertical levels, ranging from 1 to 25 meters thick with the 90 times seconds time step, starting from 1993. And the forcing is again R5, and the data assimilation scheme is the local areas of space transform Kalman filter, assimilating sea surface temperature and the temperature salinity profiles. And here, key results show that there are strong salinity gradients, which require a high resolution system. In fact, my colleagues show here that if the resolution increases from 2 miles to 1 mile, then the skill of the system is increasing. And the system will foresee some upgrades for the future version. And some of the challenges here also include the HPC requirement to integrate the system, and there are some uncertainties in the lateral open boundary data that will be used in the Baltic reanalysis. And the other plans are to have the two-way nesting using AGRIF and increase the vertical resolution and assimilate more observations, which will, of course, add up to the computational load. And my colleagues suggest to use this product to investigate the last 30 years of the Baltic Sea, interannual and the seasonal variability. And they don't suggest to use it for the small-scale events and as the storms and so on. And they believe that this is a good product that represents the inflow into the Baltic with a reduced bias in the temperature and salinity. However, there is an overestimation of the sea ice and the negative sea surface temperature bias. So I moved to the Black Sea. In the Black Sea, the reanalysis starts from 1993. This system has a close boundary at the Bosphorus. Actually, surface boundary condition at the Bosphorus Strait. This doesn't include the Azov Sea. It's using again the RL5 with the NEMO version 3.6, and the resolution is quite high here, 136 to 127 with 31 Z levels. And the data assimilation scheme is OceanVar, which is assimilating sea level anomaly and temperature salinity profiles, mostly from Argo, but also CTD and XBT. And the sea surface temperature is relaxed at the surface in order to constrain the surface. And the product shows great skill, actually, for example, this is for sea level anomaly, which is about 2.5 centimeters of error at the sea level anomaly compared to the observations. And for the future, the boundary will be in the Marmara Sea, so there will be open boundary in the Black Sea reanalysis system, and the NEMO version will be upgraded to the 4 with a 1/40th of a degree with 121 Z star levels. So the vertical levels will be fourfold. And then the time series will be starting from 1980, which requires some sort of a boundary conditions from other systems. And the data assimilation system will be remaining the same. And my colleagues here suggest that the product has a good skill for the temperature salinity, but also the mixed layer depth and the seasonal variability. And there may be some temperature salinity drifts, especially in the deeper layers. But there's applied also the large-scale bias correction below 300 meters to prevent this drift. And I move to the EB. EB has a 1/12 of a degree resolution, and they started from 1993. And the data assimilation side, along track sea level anomaly, SST, and in situ profiles are assimilated. And there's also tidal forcing in the EB system here for the reanalysis. And it will be upgraded to 1/36 of a degree in the next version, and the model and data simulation system will be upgraded too. And also here we have some computational costs that are increasing with the coming version of the system. And the availability of the in situ data for data simulation to constrain the small scales is another challenge that my colleagues mentioned. And the main strength is that this is a third-tier self-consistent data set with errors and biases for some reason or other. Mostly the poor coverage of the data to assimilate, and the resolution, which will hopefully be improved in the next version. And my colleagues recommend the users to use the data for studying occurrence of some physical processes or the evolution of heat content or some major current circulation patterns. I move to the Mediterranean Sea now. The MED system is NEMO version 3.6 with 1/24 of a degree and 141 unevenly distributed Z-star levels. And MED reanalysis starts from 1987 after 2 years of spin up. And the data assimilation scheme is the OceanWAR, which is an FCAT, 3D-WAR FCAT, assimilating again the temperature and salinity profiles as well as sea level anomaly. And the boundaries are provided by the Seaglores version 5, produced at CMCC, extends back to 1980, this product. And the rivers, 39 rivers, are multi-climatology. This system shows an improved skill against the previous MED-REA 16 system, which had a 1/16 of a degree, and the background covariances and the observational covariances are improved, and the data set has been extended to other data sets outside of Copernicus for this reanalysis. And you can look at the plots to see the improvements for the SST and the temperature and salinity profiles. And there will be major upgrades also in the MED system, upgrading to 4.2 version of NEMO without changing the resolution, and starting from 1980. And the Dardanelles is now in the current system surface boundary recognition, which will be open boundary recognition in the next version. And the challenge, and also there will be assimilation in the Atlantic box here, which is not yet available in the current product. And some of the challenges, again, the computational cost and the storage of the data, starting from the bottom here. And we are working a bit on merging different in situ data sets in order to get the best coverage that can be provided. There's a poster about it if you would like to discuss it more. And we will, of course, have difficulty to constrain the sea level before 1993. And the land boundary conditions from before 1991 is another issue, because the AFAS is provided before starting from 1991. And of course, the lateral boundary conditions starting from 80. And we need a continuously extended product. And in the current reanalysis, we have a coherent and homogeneous time series for 35 years. And there are many improvements in the assimilated observations. And we have a consistent representation of tracers, trends, and water masses, thermaline structure. We realize that we are missing the dynamical contribution to the sea level, but the steric part is quite okay. And we are missing the interannual variability of river runoffs and Dardanelles Strait inflow, as well as we don't have the Suez Canal, for example, which we are hoping to include in the next versions. And we recommend the user to use this product to study water masses, formation rates, circulation in the subbasins and tracers. As I said, for the sea level, it's not a recommended product for this version. And I move to the last one, the Northwest Shelf from UK Met Office, which has 7 kilometers of resolution starting from 1993 with NEMO 3.6 version coupled to biogeochemistry using the Era 5 atmospheric forcing forced by the Gloran in the Atlantic and from the Baltic reanalysis in the Baltic side. And this product has also, I didn't mention for some of them, we can discuss it later, but most of the reanalysis now have also the interim extensions done regularly. And the data assimilation system is a NEMO 3D bar FCAT with 24 hours of assimilation window and increments applied with the analysis incremental analysis upgrade. And the observations assimilated in the Northwest Shelf is the SST in situ, and for the biogeochemistry, my colleagues will deliver more information. And the major system upgrades will be the version of the NEMO. The observations will be that will be used, and there are plans to do the hybrid 3D MWAR for the reanalysis in the Northwest Shelf at the UK Met Office, and the resolution is being tested for 1.5 kilometers. And the challenge is the salinity bias, which is supposed to be, which is being calibrated between the Northwest Shelf and the Baltic systems, and also the river inputs. Setting the salinity 20 improves the coastal bias here. And the Northwest Shelf has a few subsurface observations, and the strength of the reanalysis is gives us a changing picture of the state of Northwest Shelf, European Shelf. And a weakness is that it is difficult to simulate the salinity accurately in this reanalysis. It depends on the inflow from the rivers and from the Baltic. And my colleagues suggest to use this product to study the trends, especially for the temperature and the circulation across the shelf, but keeping in mind that there are very few observations for this product assimilated. So this is my final slide to summarize all the challenges and messages that I wanted to deliver here. We have a challenge of computational cost in almost all the systems, and the lateral boundary condition that we want to use is another issue that we need to be aware of. And the observations that we assimilated, especially in the past decades, are quite few, so we need to study them a little bit more to get the best of them. And the land forcing, especially from river, is needed for previous years, the previous decades. And all the systems have era 5 starting from 1948, I guess now. It is back extended to 1940, I believe. But maybe tomorrow we will discuss also, we need a diversity also for the atmospheric forcing for our regional reanalysis. And thanks for your patience.
Thank you, Ali. Any questions? Any in the room?
Quick question, Ali, thanks. Is there any plan to exploit the regional atmospheric reanalysis produced by the Climate Service? For instance, for the Med and the Baltic would be, and also EBN or West Shelf could be quite straightforward. And I think it's a big effort from the other service to have to reach convection scale resolution in the atmosphere. So just
for the reanalysis, none of the experts have mentioned this plan for the future. My guess is also because the era 5 extends back in many decades. I don't know for the regional reanalysis that's the case. But I mean, I'm not aware of such an effort. Maybe some of the MFCs are already exploring that possibility too.
Any other questions? No, we have a question actually online on Slido. It goes to all the reanalysis producers, and she mentioned they have GLOFAS daily river runoff. Why we don't use them in the reanalysis? Still using the climatology. Any comments? Or Gail or James?
I answered it on Slido, but maybe you didn't see. Well, I'll just mention that that has been tried in the past in a service evolution project called Bronco. And so I was just saying that it's planned, but it needs some adaptations. So it's planned for global reanalysis, if you want to add.
Yeah, for the global reanalysis side, we plan to add 13 river in interannual, but at a monthly frequency. And why just monthly? Because why just 13? Because we have worked to debias some data coming from GLOFAS.
Yes, so we're also using monthly, mostly gauge-based river discharge. We did do a little bit of comparison. We did notice a few places where there's some differences between GLOFAS and, for example, these historical tide gauge data. So that's why we're doing that.
Also, we do have the Copernicus evolution project we're working on to have the new river runoff also. Wombo project.
Yes, and also I would like to mention that so next year a new Horizon Europe project will start. Its name is CDFD, and the aim is to introduce the among different things. Its aim is to introduce assimilation component into the GLOFAS system. And so at the end of the project, we aim to have a first prototype that will assimilate the water level coming from altimetry within GLOFAS. So perhaps, sorry, in the river. So perhaps the runoff will be also improved thanks to this Horizon Europe project. We will see.
Thank you, Jill.
Just in time for us to assimilate it.
And thank you, Ali. Thank you very much. If it's no question for Ali, we have actually two questions for Gael. The first one is, can we use the data to train the machine learning algorithm?
I guess it's a very broad question. I'm not sure which machine learning targets, but I mean, a priori, I would say yes, but it will depend on what you're trying to predict. If you're taking our 1 degree model and trying to predict Mesoscaletes, that would fail. But if you're trying to, to predict, I'm not sure, like a global signal from sparse observation, maybe you can use ECCO to train it to that effect, yes.
The next question is from Mike Bell, and I think we can have a look. This is around adjusting.
All right, so I'm reading the question. It says, how about the adjusting diapical diffusivity and Jensen-McWilliams parameter? Can that compensate for under-resolved advection in a 1 degree model for the right reasons? So I mean, the overall transport of tracers will have those two components, kind of the mean flow and the eddy term. It is possible that if somehow our advection scheme is deficient, you'd have an error in the first component, and that would be compensated by the second. It's an interesting possibility that I don't think I don't know if this has happened or not, but it's a good question, I think. Thank you.
Okay, thank you very much. Thank you, Ben. We now go to the coffee break. We come back in 20 minutes. We'll come back 11:20, sorry.
Somebody interested. Yeah.
Shopping list. You can create your own shopping list. You want coupling, you want global reanalysis, regional reanalysis, coupling reanalysis, high resolution, low resolution. You can have your own, how to say, shopping list. And we will do a survey and we'll show you afterwards. Okay, now we're going to this last session we have talked about only the physical reanalysis. Now we are going to wide ocean sea ice reanalysis. Please, Gilles.
Yeah, thank you, Chantrey. Okay, my name is Gilles Garric from Mercator. So I will present an overview of what's going on in sea ice in reanalysis in Copernicus Marine Service and in other reanalyses when it's the case. So I did this work with Annette, who is in a room, Laurent Bertino and Clément Bricot from Mercator, and Annette and Laurent are from the NERSC in Norway. Okay, so just a brief overview of what I will talk about. I will give you just an overview of what's going on in the current reanalysis system in CMIP, including sea ice state, performance and evaluation of reanalysis, focused again only on sea ice. I won't talk about the iceberg actually, and perspective with the emerging reprocess data. What we have now in terms of sea ice essential oceanic variable in reanalysis, future plans and conclusions. What we have actually in the reanalysis system dealing with the sea ice representation. So here on this table, you have all the list of reanalyses having a sea ice representation for the global, the glorious 12V1, but we have already presented this reanalysis this morning, and all the component models forming the GREP reanalysis at a 1/4 degree, the Arctic MFC reanalysis from Topaz in Norway, and the Baltic reanalysis. I have put all the, I would say, important component of this reanalysis in terms of sea ice, in terms of resolution, also to see that we are approaching the resolution where maybe the continuous flow of the sea ice maybe won't be satisfied. You can see, for example, on the ITD, on the ITD, which is the ice thickness distribution. Actually, very few models have the high thickness distribution. Have only one category on the good mesh. Only Glossy 5 and the Baltic reanalysis have this kind of representation. Almost all the reanalyses I simulate the sea ice concentration with a different method, either variational or Kalman filter. The only analysis dealing with the multivariate approach is the Topaz Arctic MFC analysis, where they assimilate sea ice concentration together with sea ice thickness and sea ice drift. Okay, and what also is worth to mention is that they all use the EVP, which is the elastic viscoplastics rheology. And they don't. We don't plan to improve that in the near future. Okay. Okay. Just to have a look at the performance of the, for example, the Topaz Arctic MFC analysis. They are assimilating the CS concentration from the CCI. They are assimilating CS thickness from a cryosat and SMOS merged product after the 2010 year, and only in winter because we don't have this kind of observation during summertime. And they are also assimilating the scattorometer data from OSISAF from 1999 until 2020. Just to have a look, just to give you an order of the performance we can achieve with this kind of system. With the Topaz 4B, they are assimilating the ESA CCI all along the time series, which was not the case for Topaz 4E. This is why, in fact, when we are comparing this Topaz 4B against ESA CCY, this is why we have a reduction of the misfit. Again, what's going on? That's, Okay, I put the wrong button. Okay. Anyway, so just to tell you that, in fact, we are, in terms of percentage, Topaz reach more or less, I would say, between 10 and 15% of errors with the CS concentration compared to the observation they are assimilated. And this is the kind of thing we have for all the analysis system. And if we do the same with the Gloris reanalyses, on the left-hand side, you have the Arctic scores. On the right-hand side, you have the Antarctica scores. What is also worth to mention that all these analyses have biases and RMS which are very stable over the period, which is a good cushion for the good performance of all these systems. We have also a season cycle of a typical range of error with maximum in summer, about 25% and 10% in winter, and which is the classical biases and RMS where you can find in analysis. We have higher RMS difference in Antarctica, which is true, and especially along the east coast in Antarctica, because our analyses are struggling to represent the covering of the sea ice summer on the East Antarctica. But a recent analysis made by Dorothea Yomino at CMCC, he compared all the models forming the grape analysis. On the right-hand side, you can see for different period of the year. On the solid line, you have the SCX extent. On the dashed line, you have the marginal ice zone. You can see that either if the CS concentration is very well reproduced, IMZ is maybe less reproduced, but the ensemble mean does a very good job. And I think we are really progressing in this kind of thing, and it's quite important because the CIS is becoming in the future more or less in MIZ state, than a really solid and compact CIS cover. Another study that I just mentioned here that made by the team of François Massoni in Louvain-la-Neuve, doing with southern CS concentration budget on different analyses with grape ensemble models, and they say they recommend the use of this analysis for further study in the future, which was a good sign. In terms of for the Baltic MFC analysis and CIs, Ali has already mentioned this regional analysis. What is interesting here that of course, they have a sort of overestimation of CIs of the Baltic Sea. But what is interesting here that they compare this CIS concentration with the ice charts and with the ice chart designed and produced by the FMI. And they produce a sort of dedicated metrics to compare with ice chart, because ice chart is not, I would say, automatic metrics, and it is done manually. And you have to define a specific metric on that. And I think this is the future of our assessment of CS concentration when we have ice charts available. In terms of CS thickness, so you have on the left column the data from a Cryosat 2 SMOS merged data, and for different months. And Topaz has assimilated this data, and you can see the effect on the right column. First, what is good is that we are able to assimilate this kind of data, which is not obvious, because actually we are trying to assimilate this thickness in multi-category model, and I can tell you this is not really obvious, and I think Eric will talk about that this afternoon. So what is good, in fact, that we are able to Topaz is able to keep memory of this assimilation of CS thickness, despite the fact that Topaz don't assimilate this Cryosat 2 SMOS data during summer break, and we can keep like that the memory, and after correct this for the winter. And you could say that the improvement is weak. But I can tell you that having this kind of correction is quite hard to have, and I think we will have to pursue in this direction. In terms of again on Arctic sea ice thickness, we are there is a lot of effort actually in the validation of this variable in terms of satellite. Here you have, for example, the comparison between the topaz Arctic analysis and the ISAT data. You can see here that for the winter and October, November, you can see that with overestimation of sea ice thickness in topaz in the Beaufort, underestimation along the Greenland Ocean. But this is the kind of bias that you can find in all analyses. And I think again, if you want to have this kind of biases in a run without assimilation, I think it's not really reachable actually. What is also interesting that in the framework of the Polar Aura IP led by Petteri Uttila in 2019, you can see the large spread of estimation of sea ice volume for these months, October and November. So we don't really know what is reliable in terms of analysis. What is good, and maybe the good information behind it, that all analyses agree that the Arctic sea ice volume has declined, but not by how much, in fact, because even for the observation, if you see the black dotted line, which is the ISAT, the other one, which is Cryosat 2, they are not overlapping over the same period. Even the approximation of ITRP based on the many observations, you can see that it is far from being the same estimation from ISAT, for example. So this is a widespread of Arctic sea ice volume, actually, in our analysis, and we are struggling, in fact, in finding the right values to give for estimation. What is good is that if I took again the estimation of glories, you see this is the blue line on the top of this old estimation. And there is a likely overestimation of sea ice volume in the old version of glories. And now with the new glories 12 V1 estimation, you have this estimation in pink in the middle of the spread. It has to be compared with the green old estimation from the very old glories version. So I mean, we are improving that because if we compare that with the estimation of biomass, which has been designed to have the trend very close to the observation, so we are stretching the spread, which is good, and we are maybe ending to find a sort of estimation of the spread with comprehensive uncertainties. There is also sea ice thickness in Antarctica, so I think it's starting. There is a lot of work actually going on in Antarctica, and there is this work of Xi et al. In 2021, comparing different reanalyses in the Weddell Sea, and to look at this the thicker ice found in Antarctica along the peninsula in southwest. You can see that again with all the analyses are struggling to represent this kind of accumulation of sea ice along the Antarctic Peninsula. Maybe the geomass data, which is the counterpart of biomass for the global ocean, there's maybe a nice work, but still, if you compare that with the ISAT data, we are far away for being able to retrieve this ice thickness distribution. But this kind of behavior are really familiar with all the analyses that we have actually everywhere. In terms of in situ data, just if you have a take-home message, I would say that we don't have really a lot of in situ data at high latitudes. I mean, they are very sparse, and I think this is a clear gap for future model development in terms of sea ice representation, and if we want to expand that to the high latitude understanding of the process going on there. These in situ data are mainly for thickness and drift. sometimes you have snow depths from aircraft or this kind of thing, but they are very rare. So it's very difficult to really evaluate models and reanalyses with the ground truth. Here you have, for example, an example of what Topaz is doing against sea ice thickness, sea ice draft from submarines and airborne campaigns, doing the ice bridge campaigns. So you can clearly see here, for example, the Arctic MEFC analysis is thinner compared to this in situ data at this location. And we are downloading this data from a very nice effort from the team in Woods Hole in United States. They are doing that for 15 years, and we are using it, and I think it's very useful. In terms of in situ again and drift, in fact, the analyses are doing well. In fact, in terms of large scale, this is maybe one of the metric which does well. Here you have the comparison between, on the left, you have the estimation of mean drift by buoys from the EABP campaign. And on the right, you have the Topaz estimation. So we can see that in terms of magnitude and also on the large scale of the pattern of the drift are more or less very well represented. Of course, the center of the pressure is a bit misplaced, but I think on the large scale is pretty nice because we want to reproduce correctly the divergence and convergence of this kind of field. And what is nice also to have on the right hand side, you have the time series of the BOs compare in green and the uncertainties associated with that, and the Topaz 4 estimation. You can see that Topaz 4 is doing well in reproducing the internal variability. The only thing Topaz is not able to reproduce is the acceleration, is a large acceleration of the spheric drift and sea ice velocity in the Arctic, which is a very good sign of the feigning of the sea ice, and also the thing that we have more and more free drift now in the Arctic Ocean. Okay. Another point I wanted to underline today is that there is a lot of data available now for the sea ice. I took the example of this reprocessed surface temperature developed by DMI in Denmark, and they are proposing a merge sea surface temperature data all over the ice and ocean surface. You have an example here for the in 2018. You can see there is a continuous field of surface temperature over the Arctic, and this is a product, I think, of a good value. You can, for example, with this surface temperature, calculate the trend, and you can see you can imagine that you know that at this latitude we are facing one of the biggest surface warming on the world. You have a plus 4.5 degrees Celsius over this period. Okay, and again for the surface temperature, it is known also that all the atmospheric analyses have important biases of the surface temperature in the Arctic. Here, the paper from Batrack and Muller in 2019 was highlighting this warm surface temperature in winter for ERA 5, GRA 55, OMERA 2, and INSEP 2. And this is due, in fact, because they are misrepresenting the snow layer in the atmospheric analysis. So if you are missing the snow layer during winter, you have overestimation of the conductivity because the snow conductivity is pretty low compared to the ice. And you have overestimation of surface temperature and overestimation of upward long wave during winter time. So we have performed an experiment where we use the 7 different atmospheric analyses with the same model. If you compare that with the observation I was talking about just before, you can see, so in black, you have the observation, and in different colors, you have the surface temperature model with this different atmospheric analyses, and you can see that all the analysis, all the experiments forced with all these analyses show a very important warm biases over the Arctic with a very high variability during the winter time. which is due to the problem I was mentioned before. So these warm biases can reach up to 2 degrees, 3 degrees in summer times. So we can imagine the impact of this on the Arctic sea ice when you want to model it. With this observation data, first test has been made in a simulation context at a DMI, and what they have found, the very first result they have found that when you are assimilating this surface temperature, you are thickening the ice, and especially at the cold pole of the Arctic, so along the Greenland, and this is the place where we are missing thick ice. And I think it's very interesting, and I think this is a way we should look in the future. In terms of snowfall, again, there was a large intercomparison made in a framework of polar RIP by Petteri and et al. And you can see that there is also a very large spread of the estimation of the snow volume against in all the analyses. For the GLORIS or GREP analysis, and this is more or less a random estimation of this kind of metrics. Many reasons of that. You can see that, for example, you have analyses using exactly the same snowfall precipitation, but they have a very different estimation. So this comes from different parameterization models, so either the snow conductivity, either the albedo, and you end up with this kind of a large spread of the snow volume. What is also interesting is that the snow depth is also highly dependent of the atmospheric forcing. You have on the right-hand side, on the differences between ERA 5 and ERA interim over this period, 91-2018. And you can see the very large difference between ERA 5 and ERA interim, nearly 2 times the difference between these two analyses. So we don't know what would be the impact of that on this simulation in the future for our analysis. There is also, I said that there is a lot of new observation data going on, and this is the case for snow depths. And a recent paper from Florent Garnier, who developed a new estimation of snow depths from altimeter and Saral, and they compared their observation retrieval with other observation retrieval, and there was also big differences between the algorithm observation. This is in Antarctica. Sorry, I didn't say that. What is interesting that for the sorry, this is Antarctica on the bottom and Arctic at the top. You can see in the Arctic you can find very spread very different estimation of snow depths all along the period, and sometimes the model is performing well in Arctic, and it performed very bad in Antarctic. So the conclusion we had in Arctic is not necessarily the same in Antarctic. This is, for example, for Mercator, we have a much less snow depth than the estimation of this observation data, but in Antarctica we are fitting well. So I mean, we have a lot of work to do to understand what's going on with these snow depths, and I think this snow depth is very important because this is the kind of thing that we need. For example, for the altimeter freebird retrieval, because there is a lot of uncertainties behind it, and the model could help in finding and reducing these uncertainties. Just to mention what we have actually in analysis in terms of essential ocean variable as a goose classification. So in terms of goose classification, you have plenty of sea ice variables. And what we have in our analysis is in green on the second column that we are able to produce because they are prognosed quantities, but there is a lot of data which are called supporting variables or secondary variable, which that we are supposed to deliver in terms of a description to get a better description of in sea ice state. And you can see that we are still it's still partial description. So, and again, the in situ representation of sea ice is really a gap, a clear gap. Okay, so I skip this one. So where we are now on the future, just rapidly that all the models are going into multi-category CIS model. They are all using the plant all using the ERA 5 atmospheric forcing. They are also planning to assimilate working, for example, for Siglors, they plan to implement the CI thickness assimilation, and there is a lot of work going on for the CI thickness assimilation. I didn't talk about it, but I think I don't in time, so okay. So I won't repeat the conclusion. I just would like to underline that there is a lot of new reprocessed data, and we should have a look on that. And it's a challenge because it's really complicated, but I think there is a large opportunity behind that. Just my message is that I think we should push to another intercomparison project for the polar, such as the polar RIP. I think we have learned a lot, as already mentioned. We have learned a lot to what are the capacity of analysis, and I think they have made enough progress to have this new intercomparison exercise. And just the last messages you can see on the right-hand side. You knew the Arctic death spiral, but now we have the global sea ice death spiral. In fact, with the big collapse of this sea ice in Antarctica, you can say that we are now maybe entering in a new mode of the sea ice representation on the global ocean, and you can see this gradually collapsing of sea ice of the global on the global ocean. And I think it's very important to continue to monitor the sea ice cover in Reanalysis and improve that. Thank you very much.
Thank you, Gilles. Maybe we move to the next presentation. Sorry, Gilles, we will have question later. we go to waves from Lotfi, please.
Okay.
Yes.
Up, down, and here. Okay. Make it faster, Vincent. So, okay. So thank you for having me. I will give some investigation related to the wave reanalysis at the global scale and the regional scale. So this work has been done with contributors, Stefan and Alice and Luna, which working on the EB MFC, and also some contribution from the regional MFCs. Okay, so the motivation of this work. So then you have seen yesterday that there is a lot of need and I think for more accurate wave product. So then so the motivation, the first motivation is to improving the wave reanalysis and focusing and to provide the best wave parameters for the wave climate studies and also downstream applications. As mentioned yesterday, I think by Melissa, so there is a very important coastal application related to run-up and overtopping, which is more related to precise input from the wave reanalysis in terms of directionality of the waves. So the update of the wave reanalysis needs some satellite wave observation reprocessed, and we wanted in the last months to look at the past missions and the current satellite missions, and this is important to have including this in the data assimilation of the wave reanalysis, the global one, in order to provide the best boundary conditions for the regional MFCs wave reanalysis. And the last, and as mentioned by Gilles before my talk, so it's really important to have now on the global scale to focus on wave ice interactions, so that we need to improve and to include in the wave model wave ice interaction source term, in order to get the right variability of the waves inside the marginal ice zone, and also having this coupling between the ocean and wave better described than we have actually. So the wave reanalysis and the wave in general, they are really complex systems. So then we have here I want to show the dependencies of the wave reanalysis. So then we have really many dependencies. So the first one is the wind forcing. At least we need a very accurate wind forcing, and currently in the global and the regional scale, we are dealing with ERA 5, but we investigated some other products like the climate regional downscaling from ERA 5, which called SERA for the European seas, and also we looked at what is the wind tack providing in terms of wind forcing for maybe the last 20 years with the very interesting product depending on scatterometers input. So we have also looked at the second dependency, which is satellite wave observation. We looked at the altimeters, significant wave height, and we have also looked at what we can improve in the new reprocessing provided by the CCI sea state in terms of significant wave height. And also we wanted to look at the past mission of directional wave spectra and the current mission, which is Sentinel-1 and CFOSAT. The third dependency is related to the current, and for the wave reanalysis, we are for the first version on the wave is for the global scale. We are using the Glorious, which is quite good in terms of including wave current interactions. And we looked at other products coming from the altimetry, like the multi-ops current data. And the last part of the dependency is the sea ice. So then Stefan has looked to how the wave model behave by including sea ice forcing from Glorious, and also by using the sea ice thickness from the Glorious. So this is the current satellite wave observation we have. You can see that we have a very I think a good era of in terms of satellite altimeters. We have 7 altimeters flying. So I don't include the HY2, but if you add HY2, 3 more, and we have a better coverage in the global scale and also on the regional scale. We have 2 missions actually giving the directional wave spectra, which is really important in terms of correction of the wave propagation inside the wave model. And the 2 missions are Sentinel-1 and CFOSAT, playing at different scale of wavelength, shorter scale for CFOSAT and longer scale for Sentinel-1. So this is an example of what we have found in the last version of WaveRIS. By using Sentinel-1 directional wave spectra, we can see that we have a very good description of the wave variability in comparison with the buoys. This is an example of a comparison at Hawaii buoy. Which give you an indication that the swell coming from the Southern Ocean is really, really well modeled in terms of capturing the right initial condition of the propagation of the swell in the Southern Ocean. An example, the color is not very well, so this is an example of the added value of using directional wave spectra. Directional wave spectra improves the initial condition of generating the wind waves, and this is really mostly in the Southern Ocean when you have a very big storms on unlimited fetch conditions, and with the directional wave spectra we get the right wave growth in these conditions, and this is an example of the bias, which is quite reasonable, less than I think in average less than 10 centimeters in the Southern Ocean. This is for 3 years of WaveRIS for the first version, and on the bottom we can see that the standard deviation, normalized standard deviation scatter index is really slow, small, in average 8%, which shows the good modeling of the waves in this really intense stormy region. An example of difference in terms of directionality. This is an example that we show that directional wave spectra improve the propagation of the group velocity of the waves, and on the bottom to the right we can see the comparison of using direction wave spectra in wave risk and the ERA 5, which is for high significant wave height. We can see that the wave risk is doing better than ERA 5, which is not including directional wave spectra. Rapidly, we investigated the climate regional downscaled atmospheric forcing. This is SERA. This covers all the European seas, and we wanted to look at the impact on EB domain. This is on the left side. You have the average difference between SERA and ERA in terms of wind speed, and you can see in the coastal area that SERA is doing better. So we have a very big difference with the ERA 5. This is quite normal because SERA is more resolving the small scale at 10 kilometers. And on the right side, you have the average difference of significant wave height during January and February of 2020. And you can see that the difference can be very strong in average, particularly in the channel and also on the swell track coming from the North Atlantic storms, and also on the southern part of the domain to the coast, the Moroccan coast and the Canary Island. So in terms of bias, we can see a very good improvement by using SERA for the EB, for example. On the left side, you have the SERA, the bias map of significant wave height in comparison with altimeter. And you can see that it's really well decreased in comparison with the ERA 5, which is on the right side, which is more strongly underestimating the significant wave height. On the bottom, you can see that the QQ plot for significant wave height is strongly improved by using SERA, particularly for the high significant wave height. This is really good. The second point we want to highlight is that using a better denoise significant wave height from the CCI seastate. This is an example. On the top, we have a result of the assimilation of such a product in comparison in the middle with the original one, and without assimilation on the bottom. And you can see that the bias on the top is really better. It's smaller than the one in the middle and on the bottom. Rapidly, we wanted to look at the past and make ENVISAT great again. ENVISAT it was the first and it was the era of using directional wave spectra in the last 20 years. So we started that with these missions. ENVISAT is providing significant wave height at the nadir and also a SAR measurement described here by the energy on the frequency scale and the direction. So we have a very long database, more than 10 years of data from ENVISAT, and we wanted to use this in the next release of the wave RIS, and also we have already used it in the EB domain. This is an example of what provide such a directional wave spectra by correcting the wave number component of each partition, which is each wave system. So you can see that here is an example of difference by mean directional spreading, which is variability in terms of the peak in direction. And on the bottom, you can see that the difference of the spreading with and without assimilation. You can see that the difference can be very strong of the spreading here on the swell track. For example, here, this is for September to December 2010. Rapidly, we have shown also, this is an example of the new EB reanalysis in waves. And you can see by using significant wave directional wave spectra from ENVISAT, we have here on the bottom the difference with the old version of the EB wave reanalysis. We can see that there is an increase induced by this assimilation in terms of significant wave height on the upper part of the domain near the channel and also on the Biscay Gulf. And on the bottom, we have a decrease in significant wave height, which indicates like a better description of the swell coming from the North Atlantic. we have to be very careful by directionality of the waves. This is an example here I wanted to highlight, which is this is a SAR, a Sentinel-1 wave directional wave spectra. You can see that in this case we have two wave partitions, and you can see an example here from field campaign from a ship measurement at X-band radar that the SAR is doing right well in comparison with this field experiment. However, by assimilating the SAR in the model, you can see that the two wave partition has been merged. This is mostly because we have less resolved the directional wave conditions. So in the next release, we will improve such a resolution of the direction with the 36 direction, which is quite good in terms of describing extreme waves and also assimilating the Sentinel-1 and also CFOSAT data. Rapidly, comparison with the current. At the top, we did some experiment by using the GLORIS, the version 2, and here the impact with and without surface current forcing. This is with the multi-ops globe current. You can see that the shape is almost the same. We have the same trend. However, we can see by zooming on the agulas that GLORIS is giving more enhanced current, which indicate like this is induced by a smaller scale in description in the GLORIS, which is a better result than the product in the reprocessed globe current data. Okay. Rapidly, we looked at the sea ice sensitivity forcing. This is an example. Sorry, is an example of to show here on the left side the forcing from sea ice from IFS ECMWF, and here is when we use a CFOSAT, for example, ice product merged with IFS ice product. You can see that we can improve the bias in the Southern Ocean by using such merged sea ice product. This is waves is really sensitive. This is a difference. This is a bias of significant wave height, and in the wave reanalysis, we need to look at this in really in particular attention. By including a source term using sea ice thickness and getting the attenuation of the waves inside the marginal ice zone, this is a kind of development have been done in the wave model MF1. Is an example of sea ice thickness from the GLORIS, and you can see on the bottom the difference for January, the average difference in January 2020. With and without including wave ice interaction term in the model. And you can see that the difference can be very strong. Here, the maximum range is 60 centimeters in average. In the Weddell Sea, particularly, and Ross Sea, we have a very big difference, showing that the model is overestimating significant wave height. And by using a source term, including wave ice interaction, we reduce this overestimation. We did some validation on this product to look at how this wave damping, sea ice, wave ice damping behaving with in comparison with the altimeters on the bottom to the right. This is Sentinel-3 passing over the Weddell Sea, and it's an example in the storm in the Weddell Sea, and you can see here the storm is turning and going south or southwest. And this is the wave height value, and on the bottom you can see the difference induced by using the wave ice interaction term. You can see that the waves is propagating before and after the big ice flow here, which shows a very interesting propagation inside the marginal ice zone. And by validating this with Sentinel, you can see that the black color shows a better standard deviation in comparison without using wave ice interaction term. Well, finally, so the key messages. So we first focus on a need for reprocessing satellite wave observation in significant wave height and also in directional wave spectra. I think CCI, C-State Phase 2, they have a plan to reprocess all the mission NVSAT, so with a better algorithms retrieving directional wave spectra. This is really important in terms of application. The second point I want to highlight is wave-ice interaction. By including this source term in the model, we can really better describe the waves inside the marginal ice zone, and consequently we can look at a better description of the upper ocean mixed layer. The third point I want to highlight is that the use of SERA, which is quite interesting and good, at least for the regional wave reanalysis. We have shown that with EB region, it is working pretty well. And improving also spectral resolution is really needed for the next wave reanalysis release. At least 36 direction will be good in terms of description of extreme wave events, and also a better wave product for the coastal applications like overtopping and run up. Thank you.
Any questions? Thank you, Lotfi. Any questions in the room? Yeah. Okay. Thank you, Lotfi. Let's move to green ocean biogeochemical reanalysis.
Yeah. What is that? No. I tried the next slide button. Okay. Well, there's this. No, but wait. Okay, so that's next. Okay. Yeah. I will talk about the green ocean and the reanalysis products in the global and the six regions. So you've seen these regions before. I think the biggest difference with the blue and the white ocean is that we have a much greater variety of models, because we can have a greater variety of models. So we actually use 6 different models, and only in 2 regions are they the same. We also have a variety of complexity of the models. It ranges from the medium complexity, which is a few functional types and several nutrients, to very complex, which I describe as something having variable stoichiometry and several types of dissolved organic matter. And yeah, so but we do not have any very, very simple biogeochemical models here. And we deliver nutrients, all of us, phytoplankton, all carbon chemistry in 6 out of the 7. Few deliver zooplankton, and then there's also a mid-trophic product, but I think that will be covered in the next talk. We force the reanalysis as the same as the physics, so it's ERA 5, but also ERA interim in some of them. Rivers is a big lack, but most of us use climatology, but I will get back to that. And then there's also nesting conditions that we use, which is mostly also either nesting or climatology. And some are actually still hindcasts, so they are not assimilating anything yet, but we're working on it. So this is the big overview of the different ones. So there's fairly high resolution for many of the regional ocean models. So the standouts here is the global, of course, because it's a very large area, and also the Arctic. And the reason why that is so coarse is that we are doing ensemble data assimilation. So we sacrifice the resolution for the assimilation. And also the period is mostly from early 1990s to 2020s, but again, the Arctic is an odd one out. We have a shorter period also because of the ensemble data assimilation. Yeah, so this is the overview of who assimilates what. It's not entirely correct, but the global model and the model in the Black Sea does not simulate yet for the reanalysis, but they do have a simulation in forecast product. And then there are a couple that simulate only physics. Actually in the Baltic Sea, they used to assimilate nutrients, but no longer, so that may be coming back. In the Arctic, we only assimilate biogeochemistry, but we also used to assimilate physics. So it's a kind of reflective that the assimilation of biogeochemistry is a field in motion, and it's so that's why we're kind of going a bit back and forth. But this is the big overview of how we assimilate. And in fact, the NEMO BFM in the Mediterranean, it is coupled offline to the physical reanalysis, so they do also in fact have physical assimilation of the physics. And the interesting thing is maybe that the assimilation of physics can both improve and reduce the quality of the product. So in some cases, we can have instabilities that cause upwelling of nutrients, for example, along the equator. The Northwest Shelf saw some deterioration in the biogeochemistry when they assimilated physics, while in the EB region, in the Berian Shelf, they saw that an improvement in the vertical profiles of nutrients and oxygen when they assimilated physics. So very different. Yeah. So the variables, again, a little more detail. So mostly nutrients. So nitrate, phosphate, silicate, and iron for the global. We have phytoplankton, biomass, and chlorophyll. We also provide primary production and attenuation coefficient, which is, depending on how much phytoplankton there is in the water column. We do not yet have colored dissolved organic matter in any of these yet, so that would not be accounted for. Oxygen, of course, carbon chemistry, and a few of the centers provide zooplankton. But I just want to point out that this is a subset of what we do in the model. So, for example, we do not provide functional types yet because it's also very difficult to validate, but it could be done. So. Yeah, so I put some colors here from green to orange, but it's not really reflective of the quality of the product. It's more reflective of how many observations do we have. So for nutrients, we have both climatologies and many in situ profiles. So, but of course restricted by, because it has to be collected by ships, it's restricted by region and by season as well. For phytoplankton, especially chlorophyll, we can have good coverage in space because we have remote sensing data. And for carbon chemistry, there's also been a lot of data collected over a long time. So I think we can also validate well. However, when you look at the quality, chlorophyll is very challenging to model correctly in space and time because it's quite variable and patchy. Primary production, there are very few measurements, and there's a sparse data, and the same is for zooplankton, a very sparse data. So, yeah, so that's just two examples of, there's just two examples. Like you can see, if you compare the long-term mean of the product to a satellite, then you can have a very nice result. But if you compare, yeah, that's not the point. Yeah, no, it's just two examples from the quality. So this is also the comparison of oxygen from the Black Sea, showing the blue one is the observations, blue back is observations, and yellow red is the model. Yeah, so just showing how we actually show the quality of the model. If you look in the product description, there's also statistics as well, but I thought that would be more boring to look at. Right. So strengths and weaknesses. I think the fact that we are so diverse is both a strength and a weakness. in general, I guess the higher up the food chain you go, the more uncertainty you have in terms of parameterization and also less observation. So I would say that the higher up the food chain, the more uncertainty on these products, although we do not quantify that specifically. Several regions have very high resolution, which I think is good, is a strength. And also the fact that regional knowledge has been applied when tuning and setting up these models is also a strength. Weakness is a nutrient load in rivers. Is really either annual values or climatological values. The Baltic is the only one that has a time series of that. But it's also really lacking. It's something we do not have on shelf. It's not because we haven't implemented it, it's because it's not there. And then not all the systems assimilate the biogeochemistry or even the physics yet, so that there is a lot of room for improvement. And we can see that the integrated values have better quality in general than if you pick just the point in space and time, you can't really expect it to be of very high quality. Yeah, so that's what's that supposed to illustrate, actually. So this looks very nice, right? But when you look more closely at it's much more difficult. It's a really hard test for the model to do exactly the same in space and time, although this looks pretty good, actually. Right, so what's about the recommendations for data? I thought that was quite a difficult question, but read the quality documentation. I wrote that before somebody said yesterday that they didn't read the quality documentation, but I think it's a good idea to read it before you use it. And then I think we have this very nice tool online with when we deliver the data to explore the data, and it's very quick. Like yesterday, I just did it. So for example, if you want to set up a regional model outside Africa and you want to nest it into the global model, you can quickly check how does for example, oxygen look in the global model. Does it even have the oxygen minimum where it's supposed to be? If you have that regional knowledge, it's very quick to check. So I think it's something that can be used, and you can even, in those regions where we have more than one model, it's possible to plot both models in the same time, so you can look at two models. I think for some of the variables where we have really sparse data, for example, zooplankton, and also higher up the food chain where we don't have proper closure in the models, it's uncertain, for example, with respect to trends. Like you cannot really confirm with observations whether these trends are something that's in the models, like the reanalysis, you assimilate, for example, physical data, and the amount of physical data has increased a lot over time. So there's all these things to consider when you analyze the biogeochemistry, and especially when you go a bit higher up the food chain and use variables that have very sparse observations. Yeah, and then I thought, well, why not check two data sets? If you are in the regions, why not check two data sets to see, if they are like worlds apart, then maybe you should be a bit skeptical about applying them. Yes, so there are many things. I don't know how far in the future I was supposed to go with this future plans, but there are some immediate plans, at least to increase the resolution in the Arctic and EB. We also start to use more boundary conditions from each other as the data is becoming better and better available. That's a nice thing. And including carbon chemistry at all for one of the centers, and then starting to assimilate, in fact, also some carbonate data in the global. Yeah, and then include more nutrients, that put the nutrients back in the assimilation for the Baltic, in fact. But there's this cycle where we continuously improve these models, right? And then often the improvement first comes in the forecast, because it's a big mission to rerun this reanalysis. So yeah, there's many improvements that's happening. And one of the things that happened maybe in the last 2 years is we got 2 large EU projects, and for a long time we're thinking like, oh, we have this big diversity of models, but how can we kind of play work with each other when we all work on different models. And then we had two projects, Seamless and Necton. And what happened in those projects was that in Seamless, most 5 of these models were coupled via a common coupling framework. And then in Necton, we are doing the 2 last ones, which means that we can better rely on each other's developments. So that's very nice. And especially, for example, ERSEM and BFM are already a modular models. So you can more easily take advantage of parameterizations and model formulations that are being done for different things. The second thing that happened is that this modeling framework was connected to the data simulation tool PDA. Am I doing bad on time? Okay, 2 minutes. Okay, that's fine. Yeah, so that's the second thing that happens. And then there's also this one-dimensional data simulation tool that we can really use to explore how different observations, how simulating different observations in different models, how they react and intercompare them. So I think that's something very useful that we can learn from in the future when we want to redo this reanalysis with new tools and with assimilation. And then I think I went too far into the future with this. So I think we could just skip that. And I think we will talk more about the future later. And yeah. And thank you to everybody who's doing all this work. I know I should probably have, I think it's a lot of work behind all of this. And so all of this, big thank you.
Thank you very much, Annie. Quick question from the room. The other room.
Just a quick question, sorry. I thought you were in... Okay, that's a moment. I thought you were intending to use also optical properties for assimilation, but I don't see it in the future, the near future. I thought they were already assimilating optical properties in the Mediterranean, but I see on your slide that it's chlorophyll. So what is the status of this type of assimilation?
It's possible that it is in the forecast that they're doing that, because
as far as I know, it is in the forecast that they're working on this, and they will release. This will be in the operational system that will be updated in November.
Very, very good.
So we can note that it usually starts with the forecasting systems, and then that feeds the reanalysis.
Okay, if no question, we move to the next. Thank you very much. Next one is higher trophical level reanalysis, if I can go. I'll leave, please.
Hi, okay. Thanks. So we will now speak about fishes, and I will present the microRIS product, which compute reanalysis of low and mid-trophic levels. Low and mid-trophic levels, zooplankton and micronecton, are 2 different levels of the food chain, which start with phytoplankton. Then we have zooplankton, micronecton, and then top predators. The micronecton represents organisms that are able to swim. Zooplankton just are able to drift. And micronecton represents organisms that are less than 20 centimeters. no. So to produce this reanalysis, we use the spatial ecosystem and population dynamic model, CPODIM, which is developed at CLS and CPS. And this model is based on a set of differential equations, which is advection, diffusion, and reaction equations. I said a set of different equations because the population of organisms are discretized and with age, and we have one equation for one cohort, okay, a daily cohort. These equations are forced by temperature, ocean currents, and net primary production. And the temperature, the current controls the transport of the organisms. The temperature controls the development of organism, and especially it controls the what we call the recruitment. That means the age of maturity, and also the mortality. You can see here in these figures, you have the time of development, which depends on the temperature. So when the temperature is coming cold, the time of development is longer. And for the zooplankton, we consider one functional group of zooplankton. And for micronecton, we consider 6 groups of organisms. By groups, we mean that all taxa are grouped together. That means fish, squid, crustacean are all grouped together. We don't make any difference between them. And we consider for micronecton some organism as a nictemeral vertical migration. And we consider 6 groups of micronecton because we consider 3 pelagic layers. So the first 3 groups stay during all the day at the same layer. And we consider groups that migrate between layers during the night and day alternation. Okay, so you have 6 groups of micronecton. The net primary production is used as a source term in the equation, and we do not modelize the early stage of development of organism. So we just simplify the model by considering that the first cohort is a part of the net primary production. So each group receives as part of this net primary production. Okay, I will show you 2 examples of the use of micronecton to study the behavior of top predator. And yesterday Tony showed a good example of the use of micronecton for studying turtle movement. At the left side, you can see an example with an elephant scene that is around Kerguelen, Iceland. In this figure, the color represents the temperature the animal experienced during its trajectory, and the black dots represent each capture attempt. And so you can see that the capture attempt fit with. You can see that the depth of the capture attempt depends on oh no, sorry. No, I just say that the elephant seal target some specific layer, and there are these specific layers that we modelize in CPODIM. And in the right-hand side, you can see a similar example with a big eye tuna in the Northwest Atlantic. The big eye tuna stay at the first layer during the night, and in the deep layer during the day. And here you can see, but you can't see very well, sorry, but in this acoustic transect, you can see the migration of the microneedle, but you can see very well, sorry. Another example is a publication of Lambert that they were able to produce maps of probability presence of cetacean in Polynesia and in Indian Ocean. And they use micronecton as a key variable to produce these maps. And so you have the other example with the turtle that I will add in future presentation. So how we produce this reanalysis, as I said, we use some physical and biogeochemical forcing terms. So the physics comes from the GLORIS 12 reanalysis. The net primary production is computed from the chlorophyll A globe color product together with the SST of NOAA and solar flux from NCEP. We use the VGPM algorithm to compute the NPP from these variables. We also need the aphotic depth, because the depth of our pelagic layers that depends on time and space depends on the aphotic depth. The problem of using observation as forcing term directly in the model is that sometimes we don't have data, and especially for NPP, we don't have, or chlorophyll A, we don't have data during winter at high latitude. So we use, we compensate this missing data by the PSCAS model. So what are the strengths, weakness, and needs? So the strength is that we have a daily spatial distribution, which is and at high resolution, which is unique. We have global coverage of these densities. We show that prey densities are a better proxy than chlorophyll A or NPP for application, and particularly to study the behavior of top predators. And as we discretize the population into different age, we also capture the dynamic of the population. Well, we have two problems, two main problems. The first one is the high latitude. For the high latitude, we have two problems. The NPP that is not well done, not well estimated, and also, but it is for historical reason, but our transport scheme at high latitude is not very good, so we plan to change it next year. Another problem is that we don't have enough quality data to estimate the parameter of our model, and especially for the parameter that tune the part of NPP that will enter into our first cohort. So that means that the absolute biomass is maybe not well estimated. So it's better to if you want to use this product, it's better to use relative biomass between, for instance, between different functional groups. And also you can use it to by studying or taking into account the structures, which is actually very interested for the behavior of top predator, for instance. And what we need better quality data. We need better NPP at high latitude, good physics, temperature and currents, essentially. So I will show make a focus on micronewton data. We have three main types of available data. The first one is troll sampling. The problem of troll sampling is that it depends a lot of the gear that is used to collect organisms, and there is a high bias that depends on the region where the data is collected. So it's difficult to homogenize the data to be compared with our results. And also it's extremely costly. The second type of data are the acoustic data, which is collected by Transect. But the problem of this data is poor correspondence between the signal and the biomass. But we can use it as a presence data. You can see here very well the migration between the layers during day and night. And actually, we used this kind of data to better estimate the depth of the pelagic layers. So next year, we will not use the aphotic depth anymore, and we will use the new model we infer from machine learning algorithm based on this kind of data. And the third data, available data, is environmental DNA. And we hope this kind of data will be useful to estimate quantities. But we think that the better solution is to use different data at the same time in order to well calibrate the data. So what our development plan? Well, the main ones are the better transport estimation, a new estimation of pelagic layer depth, and we still trying to collect data from literature and Transect, and we still have the idea to improve the parametrization and the validation. So here is our small teams that are working on the CPONIM model and the application, and you can have access directly to our product. And that's all. Thank you for your attention.
Thank you very much. Any quick questions? Any question? No?
No, I was saying maybe you can take one question before the lunch, but
exactly.
we probably have to move on. Yeah, thank you.
No question.
We'll go back to the questions.
Thank you very much. We can quickly go through the Slido. There's one question about the sea ice assimilation in Baltic. What kind of observation have been assimilated in sea ice in Baltic? Any, yeah, Baltic.
I don't remember, but I think this is the CS concentration from L4. Yeah. But in fact, they. Oh, you are here. Sorry.
What kind of sea ice observations you have
We don't
assimilated in
assimilate
Baltic?
in the reanalysis.
Okay.
Yet.
Good. Okay. In focus. Okay.
Focus.
Initial-
Concentrations. Yes. Yes, ice concentration.
Okay. The other one is the altimetry data. In Mediterranean, you assimilate altimetry, but it may not be in the Baltic. Is that correct?
Yeah, along track. In the Mediterranean reanalysis, along track altimeters are simulated, and in the Baltic, I don't know, not
Okay,
yet.
yeah.
It's, yeah.
Okay. Thank
SSTs are simulated, I believe, in the Baltic.
Thank you, Ali. Thank you very much. Thank you very much on the participant online. We will be back at 2:00 in the afternoon. During the lunch break, please go to our slide.com, put the number 3628-533, or you scan the code. It would be nice to have your opinions. What kind of products you would like to have? We have a shopping list. You can create your own idealized shopping list. We come back at 2:00. Thank you very much.
Thank you, all speakers.
Thank you, all the speakers
thank
here.
you, Chairperson.
Thank you. The lunch will be downstairs.
The lunch is downstairs, yes. And that's all.
Yeah, this one.
Faut que je fasse en portugais. Okay, welcome back to the Ocean Reanalysis workshop of the Copernicus Marine Service. Now we are starting the session on the evaluation of strengths and weaknesses of the reanalysis, and we will start with wave reanalysis and Joao Morim. Please.
Good afternoon, guys. I'm going to be presenting global reanalysis based wave products, focusing on extremes and their uncertainty. This is work conducted internationally by a group of scientists that are part of the Coordinated Ocean Wave Climate Project, COWCLIP, and supported by NASA and UCF. So let's go into it. So an introduction. I'm going to start with that. So why are waves important? I'm just going to start simple, and then I go from there, just to give a brief context. So waves are a key driver of coastal flooding and erosion at multiple time scales for many coastal regions. And also they pose a risk to infrastructure and can disrupt industry operations as well. We have an example here of erosion and flooding in Malibu, United States, California, and in the North Sea, large wave approaching a oil rig platform. So how we model waves using atmospheric reanalysis data? I mean, I assume many of you guys know, but for the ones that don't, we have atmospheric reanalyses being global or regional, and the wind fields associated with them. We have several products available, and we can, through wave modeling, simulate the wave fields, wave reanalysis when coupled, and hindcasts when run standalone, and we get the wave fields across the ocean. So that's the basic step to obtain wave fields from wind fields. But this gets a bit more complicated. So going through the modeling process, we have different levels of uncertainty. The first one is the wind fields, right? On the top of the pyramid, and we can have wind fields from ERA 5, ERA interim, NCEP and CAR, CFSR, GRA 55, or MIRA 2. And then we have a second layer of uncertainty that is the numerical wave modeling, where we can have different numerical wave models with different schemes, physics, sea, ice, forcing as well, and we can give it different bathymetry and also have coupling issues related to it. So the single arrow, it means is a standalone forcing, and the arrow with both ends, it means is a coupled, can go both ways. And then we still have a correction and validation procedure, which we can validate against different data, correct against different satellite measurements or databases, using different historical periods for correction and bias correction methods, etc. As we go down on the pyramid, we see that the envelope of uncertainty is getting wider and wider, right? Which is this. So going to the next one. So now I will jump into what products do we have out here that have been using globally. I'm going to be focusing on global. And so what we have in 2022, actually, we published an ensemble of reanalysis driven wave products covering a standardized wave period of 35 years between 1980 and 2014. That included an international collaboration that led to all these products being put into an ensemble, a standardized ensemble. So over here we have the different forcings that were used, MIRA 2, MIRA 5, etc., etc. And over here we have the different products that were obtained from these wind fields using different wave models, configurations, forcing, etc. And over here we have the ECMWF ERA 5 and ERA interim wave reanalyses, which are coupled. These ones are standalone. And then we use some standardized codes to actually compress everything into the same historical period, 1980-2014, the same spatial coverage, and assess a standard set of variables like wave height, wave period, wave direction, and the statistics associated. We referenced according to other initiatives like Cordex, and we got the final data set nicely gridded and ready for use across 14 products. So right now, I'm going to be talking, now that I've established the data set that we are using, I'm going to delve into the extremes, wave extremes, and the uncertainty related to those in the context of the modeling process and the reanalysis that we have been looking at. So over here, I provide you estimates of 50-year return period wave height, so a likelihood of an extreme event. Over here we have the color bar going from 0 to 20 meters, I believe, yes, for each product that I just spoke before. I know it's not very legible, but online I'm sure you guys can see it. So we calculate return periods of wave height for each global wave product using 35 years of annual maxima. We use just simple GEV, generalized extreme value distribution, or simplification of it with the shape value equals 0 for a Gumbel distribution. We tested different extreme value models, but that's not the point. The point is notable difference between storm-driven wave patterns depending on which product we actually using. So we can see, for example, just comparing really simply, we can see that if Remer's CFSR forced and the Euro 5 reveal distinct 50-year return period patterns, spatial patterns in the Pacific. That's very clear. And in the Atlantic too, near Europe, etc., etc. More of those, you can see like particular patterns as you go through them. So then I decided, okay, let's intercompare the N-year return period, 50 to 100, against buoys, long-term buoys, right? So I picked up a bunch of very well-known locations: San Francisco, Port Canaveral, Boston, Hawaii, Yokohama, and Sydney. I know you cannot see the shading, it's gone. But you can really tell, I don't know if you can, but I will explain. So over these little plus signals are the plotting positions, which is basically the observations. And the dashed line is the fit of the extreme value model, which should approximate those positions. When it doesn't, it means it's not appropriated. For example, Port Canaveral, it goes a bit up. It means probably you should use a GV. But again, that's not the point. The point is each of these circles represents a model that is on the legend. And you can see the spread across the models for each return period. 2-year return period, 5, 10, 25, 50, for the different locations. Look at Yokohama. It's crazy, right? So as you, for example, you select a 10-year return period and you can have a 8-year meter for this specific product, but this other one gives you 6 meter and the other one gives you 5 meter. So which one is right? Big question. So we find considerable spread among estimates from different products at TC and non-TC, meaning tropical cyclone, non-tropical cyclone regions, and the spread considerable larger for events with lower frequency and high risk, that is 50 or 100 year or 500 year. So this is really critical what we're looking at here, because this is going to impact everything else, like wave setup, wave driven flooding, etc., etc. So moving on, what we did here was we looked at the absolute error of each product and the significance against long-term buoy observations. So I know it's a complex figure. On the color bar, we showed the number of models where the central, or the number of times the central estimates from the model falls within the confidence intervals of the buoy. So if it falls within the confidence interval of the buoy, we assume, okay, it represents more or less the observation. So the point is to show that depending on the dot you have, on the location that you have, you actually have a high variability of how many products fall within the confidence interval of the buoy. These are the summary. So fall within confidence interval for each region. You can see big differences between the products and big variability between regions. The absolute error as well. So comparing the central estimate of the buoy against the central estimate of each model, you can see as well the colors relate to the previous legend. I didn't have space to include everything, but you guys get the point. The point is the high variability in the error, and there is no absolute model that is better than the next one. It really depends on the location, and it really depends on the forcing. So having said that, we conducted a clustering analysis of N-year return period estimates. That is for what? To understand which models are closer to each other regardless. It's kind of like recognizing a pattern, right? So I know you can't see really well, but there is color in here and there is color in there. This is kind of like an orangish, this is a greenish, and this, I can't remember, is purplish. And basically when you cluster these models together, what you found is that the extremes are clustered based on atmospheric forcing. So products with the same forcing, so this is CSRO, CFSR, GAU2, CFSR, EFREMER, CFSR, GRC, CFSR, they all clustered together here. While the ECMWF products, Euro 5, Euro Interim cluster here, and the Euro 5s cluster here, and this Euro Interims cluster here. That tells me that the atmospheric forcing is what determines the outcome that comes from the wave simulations. So what we did, on the top, we have the cluster mean. So the mean of each cluster, this is cluster 1, cluster 2, and cluster 3, 1, 2, 3. This is the mean of each cluster minus the mean of everything. So we can really tell the differences. And on this one, we can see that CFSR-based products or driven products, they tend to overestimate the ensemble. These ones, they overestimate in tropical cyclone regions and underestimate elsewhere. And this one underestimates almost everywhere, the ensemble, right? Because we don't know the truth, because we only have buoys in a certain number of spots. While in this one, it's very interesting. This one is the difference, the maximum difference between the max and the minimum. So the furthest away products within a cluster. And we can see that it varies from 0 to 3 meters. So these differences are not due to the winds, are due to the waves, because the winds are the same, right? So when I look at the intra-cluster, I'm looking at what else does it varies. I'm talking about sea ice forcing, I'm talking about wave physics, I'm talking about bathymetry, I'm talking about all of the other components except the winds. And we can see it's still substantial. So after this, I decided, okay, we have a lot of uncertainty in these models. How does the uncertainty compares with the projected changes in extreme waves for 50-year return periods, let's say. So I didn't present here because it was a lot of information, but we published an ensemble of global wave projections based on CMIP 5 models, 150 models, projections. And by comparing the projected changes that we got for RCP 85, like being a high emission scenario, so a worst case scenario kind of thing, we can compare with the present day uncertainty, which is the uncertainty that we just saw that between the models, right? And in this bottom one, we compare the uncertainty in our projections with the uncertainty in the current projections. So this is the climate change signal against the present day uncertainty, and this is uncertainty versus uncertainty. Now, the color goes from 0 to 2, being 1. If you have 1, they are the same, right? If they are less than 1, it means that this one is bigger. And if they are bigger than 1, this one is larger, the climate change. You can see clearly that is all blue, mostly. Blue means that our current uncertainty is actually exceeding the projected changes in waves that we see. Uncertainty outweighs climate change signal across 80% of the global ocean based on the CMIP 5 based projections for waves. And uncertainty associated, on the other hand, the uncertainty associated with the projections dominates the uncertainty in the present day. That makes sense because, you know, uncertainty in projections are pretty high, except in the tropical cyclone regions. And one, I guess a lot of people would ask, well, how is that possible? Tropical cyclone region should be the regions where we have most uncertainty for the projections. The fact is CMIP 5 models miss a lot of tropical cyclones or miss them all. So you have no change. So because you have no change, your uncertainty in the present is actually higher. This explains this. The point here is to focus on the fact that there is so much uncertainty between these products that have been developed within the last 15 years that is that substantial that it outweighs the climate change signal even for a big scenario. That doesn't mean the climate change signal is not important. It just means that both are important. This is transferring the same results to the offshore gas and oil rigs and to the coastal ports. So there are two legends. The first one is basically the climate change signal over the present day uncertainty. If it is bigger than 1.5, between 1 and 1.5, 0.51, and less than 0.5. So anything that is purple or orange, it means that the present day uncertainty dominates. And the size of the circle is the combined uncertainty, which is at the end of the day is what we want, how much uncertainty. So this is very important for coastal scale modeling, relying on atmospheric and oceanographic forcing, right? Now, conclusions and path forward after these results. So there are many reanalyses currently available. However, users need to consider a few things. One of them, skill can vary drastically depending on product and location. There is no unanimous product. Extremes differ considerably between products, particularly within TC regions. The considerable uncertainty amongst current products often exceed climate-driven changes. No robust conclusions can be drawn from single product-based analysis relying on extreme wave fields, and uncertainty associated with wave flooding via wave setup can reach up to 0.5 meter on average, being comparable to other extreme sea level components like storm surge, tides, and low-end projectile sea level rise, which is 0.5 meter. This is very scary. Future path. Improved reanalysis-driven wave products could benefit from development of regionally downscale wave products that can more reliably resolve TC systems and associated fields, improvement of spatial resolution within coupled models to resolve nearshore shallow water physics and coastal features, expansion of the global wave buoy network to support the simulation and validation, especially extreme wave height, frequency, and direction. That's a new study that just got published by some folks from the US Army Corps. That's pretty nice. Data set of wave buoy data. And implementation of spatial temporal models, let's say Bayesian hierarchical models that can produce observationally based extreme data at unobserved sites where we have no observations. And to conclude, in the last minute, this is the latest paper from the community of waves. It's called Wave Climate Change and Their Impacts. Just got accepted in Nature Reviews in Earth and Environment. It's a compilation of all the findings in the present day and in the future, and it describes really well the state of the art, including comparing the response of wave fields to different teleconnection patterns, including ENSO, etc., depending on the product. And also it compares trends between the wave reanalysis that we have and wave hindcasts with satellite, putting together 10 years of work that this group has done. So thank you very much, guys. Appreciate it.
Thank you very much. We have time for a quick question. Yes.
Thank you, Joao. You mentioned that there is some atmospheric relationship related to uncertainties. However, how do you deal with some of the data are calibrating the wind forcing? I mean, they use some relationship already to scale the wind forcing before using it in the wave model. So how do you deal with that? I will not say which sentence.
Okay, so for example, let's talk about the Framer CFSR. My colleague Justin, he calibrated the CFSR, correcting biases in the Southern Ocean using satellite data, which obviously changed the original CFSR wind fields. And that's part of, not answering directly your question, but that's part of uncertainty goes into it. I guess there is no really a right answer. I mean, it's known that, for example, the CFSR reanalysis have bias issues, especially after a certain period. I'm probably not the best guy to explain what is the best method to correct the winds as far as they come from reanalysis. And as other colleagues like Justin are way more experienced than me in that, what I can say is that waves are complicated because we need to correct the winds as best as we can. Some centers do not do, some others do, and then you might have to correct the waves. And also you can assimilate waves into the wave models. So there are another layer that can add to this. So I know I didn't exactly answer the question, but this is my take on what's the best approach to deal with something like that.
Okay, thank you. So there's a question on Slido where I was. Okay. Do you use this data, satellite data to validate or feed your analysis? You only mentioned atmospheric satellite data in your talk. So that was a question about data assimilation of satellite or validation using satellite data for seawater.
Again, so first of all, I didn't develop any of these products, but I do know the people that did. I believe some of these products have assimilated satellite data. Which ones, I don't know, like what type of satellite went into it exactly, I don't know, because I don't remember on top of my head. It's a lot of products. So I cannot answer that question.
No problem. Okay. So maybe we can now move to Andrea's talk. Thank you very much, Joao. We will go on with discussions later. Okay.
Thank you.
So Andrea for the blue physics, for the physics.
Yeah, my name is Andrea Storto. I work at CNR ISMAR in Rome. I acknowledge also contribution of many colleagues in the slides and some material that I will show that you can read here. So my let's say perspective on this on ocean reanalysis is mostly to focus on their ability to monitor the climate in a very general sense. And for instance, for ocean warming, there are, of course, complementary approaches, model simulation, statistical mapping, proxy data, geodetic approach, and recently AI reconstruction. At the same time, reanalysis can be used for many other things, as we know. Downscaling exercises, initialization of forecast system, and process-oriented studies. So if I go back to some intercomparison exercise we perform in the framework of ORIP project, I would say a few years ago, actually, the reanalysis vintage was, at that time, was around 2010, even though publication came roughly 7 years later. You can see on the left column, in particular the bottom left, no, oops. Okay. 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 Yes. So the here in the bottom left, you see the difference of correlation against independent observation of steric sea level between an ensemble of reanalysis and an ensemble of objective analysis. Meaning that, especially in the Southern Ocean, reanalysis as an ensemble outperformed the objective analysis. If you look, however, at the trend of the global steric signal from this ensemble is quite catastrophic, I would say, if you put it just focus on the dispersion of the different. Of course, it's particularly challenging because the global allosteric signal is impacted by the freshwater imbalance coming from the atmospheric forcing. It's a really global integrated value. However, I also want to point out on the right side, the right column, the ensemble spread of the GREP reanalysis in the dashed line compared to the ensemble spread of the subsample of the ORIP intercomparison from the same producing center as GREP, meaning these are basically the predecessor of the GREP reanalysis ensemble that is now in the Copernicus portfolio, meaning that if we believe, and I mean, we can discuss a lot, but anyway, that the consistency between reanalysis increases with the accuracy, then we have an improvement with the last production, and was something that also Gilles mentioned this morning about CIs. Okay, so my main concept of this talk is to try to justify or let's say push the use of larger ensemble in the reanalysis production. And this is mostly, I mean, for a few reasons. First, because we need uncertainty to quantify the uncertainty of reanalysis, and this is particularly important when we extend backward before the Argo period, our reconstruction. So in order to provide really a level of accuracy. Another aspect is a bit more technical, but this will allow to have flow-dependent error covariances in data simulation, which is also very useful for the accuracy of the reanalysis themselves. And then when we also turn our system into a probabilistic, there are good argument and good proof that also the ensemble mean state improve. So the skill score of the ensemble mean. Here you can see the root mean square error in black of the ensemble mean of grep and the ensemble spread in red. So they look quite different, but when you normalize the two lines by their respective mean and standard deviation, we can start seeing that there is a clear information from the ensemble spread which resemble quite well the deterministic the ensemble mean error, especially in terms of its temporal variability. One topic that is now quite mature in the ocean modeling community is the use of stochastic physics schemes, which of course are enable a number of different applications ranging from predictability, energy cascade rectification. But in this context, it's quite important to mention that these developments really allow ensemble analysis to account for model errors. And two results I want to show about stochastic physics package scheme we have been developing for NEMO is the ensemble mean rectification. I cannot go into details of the stochastic scheme, but this is just to say that using a different stochastic scheme improves the mean bias. This is verification against glider data in a regional model. So the black is a control unperturbed and the other different stochastic scheme where we can see that the ensemble mean improves. At the same time, in global experiments, we also see a quite significant increase of eddy kinetic energy at mid-latitude in both 1 degree and 1/4 degree simulation. Here is the zonally average eddy kinetic energy in control simulation in black and in simulation with the stochastic kinetic energy backscatter scheme. So you can see quite consistent increase of mid-latitude EKE. Okay, for the people using NEMO, I just want to mention that together with Julien Lesommet, we are chairing a NEMO working group on machine learning and uncertainty quantification, and we aim to harmonize all the developments within the NEMO community about stochastic physics scheme in order to make, I mean, possibly increase the possibility of perturbation in next version of NEMO. Another aspect I mentioned is about the possibility to use hybrid background error covariances, which are basically combining a variational stationary covariances with ensemble derive. And one motivation, if you look, for instance, at the ensemble spread from the grep reanalysis in the tropical belt during neutral and Niño and La Niña years, You can see for El Nino here, and there is the increase of spread compared to neutral years in the around the thermocline is really an indication that there is some regime-dependent modulation of the errors that can be exploited in Ensemble analysis. And if you look, for instance, at the hybrid weight, which means how much I mean, in this case, 0 means purely ensemble covariance is 1 purely stationary. We have an increase of performance no matter which weight we give, with optimal result around 0.8, except when we use fully ensemble covariances, because the grep system is only for members, so it's quite small. And same results we have for when we go to regional regional simulation. Okay, the last part is about the possibility of extending reanalysis onto a centennial scale. We did some exercise comparing different families of century-long reanalysis with colleagues from CMCC, CMWF, and Texas A&M. We found out that here you have some comparison. The black is this multi-reanalysis ensemble. CMIP is in red or yellow, which are quite steady behavior. By construction, we cannot study the decadal variability with this product. And with an ensemble of analysis, we have consistent results with other independent estimates. And this motivated us at CNR ISMAR to start looking at centennial reanalysis, building a reanalysis system which actually penalize the spatial resolution, if you want, ranging from 1 to 1/3 degree resolution, but extending not only the temporal dimension, as I said, but also the ensemble dimension to 32 or 48. We have some other characteristics like deep ocean bias correction to AI reconstructed fields, also daily discharge from the bias corrected Japanese reanalysis JRA 55. There are more details in a new website that you can see here, and also the poster here. I cannot go too much into details, but we use this system both for what we call contemporary stream forced by era 5, but also in a quite long stream dating back the second half of the 19th century, forced by 20 CRV3. And we devote quite efforts to design ensemble system perturbing what we believe are all the main sources of uncertainty. So the atmospheric forcing with different members, the SST dataset, also in situ observation dataset, either from UNIV, World Ocean Database, or IQUAD, perturbing initial condition, the bulk formulas, and also adding on top what I mentioned before, stochastic physics. Okay, a couple of results I want to show, especially in terms of uncertainty. You see here consistency in terms of long-term diagnostics like trend and acceleration against other data set. There is also some more enhanced variability that with mostly data denial and system denial experiment, we found out that they are actually not an artifact of their analysis system, but really are depending on the high frequency of the data assimilation, like 10-day compared to typical data set statistical mapping of observation, which are usually have a lower temporal resolution. This, as I said at the beginning, this ensemble allows us to really have a look at the. It doesn't work. Oh, okay. To look at the uncertainty in terms of ensemble spread, and for instance, what I show you here is the oceanic content uncertainty normalized by the standard, by the variability of the oceanic content, so in percent. In the global ocean, we see around 40% of uncertainty before the Argo period, dropping to around 15% after Argo, with an effort by the GIGOS community that is an ensemble of objective analysis. It's like lower, less steady, but lower normalized uncertainty before and then is close. By clustering the ensemble member based on their sources of uncertainty, we are also able to rank the sources of uncertainty depending on the grid point and so on the region. What we found out in terms of significantly prevailing source of uncertainty for the oceanic content estimates that the observation processing uncertainty, mostly the XBT for rate correction, prevails at mid to high latitude and SST at low latitudes. This doesn't consider the model error, however, but only the input sources. So, and we start to extend this system, as I said, to cover the second half of the 19th century. We have some pilot experiment that will be extended to a 48 ensemble system covering 1871 to date, actually to 2015. That is the availability of the 20CR forcing. What I want to show here is the heat content variability in blue for the ERA 5 force reanalysis, and in green for the historical. There is a very good consistency overlap. This is an indirect proof that even few observations are able to shape the oceanic content variability, that the model errors and drift are not compromising the results. And then we can reconstruct, of course, this is compared to observation El Niño index, no surprise because the observations are assimilated. However, we reconstruct also the super El Niño event of 1878-79. Okay, the last slide is about reducing the uncertainty, and I think Jim mentioned, Julian mentioned yesterday, the possibility to use analysis increments, and we start also working on using analysis increment to learn the state-dependent systematic errors in the NEMO model. So it's just an example of bias reduction, for instance, in the upwelling region, 50 meters temperature. Main point here is not to talk about that, but to stress that ensemble reanalysis extended back in the past are also important as a source of data set for more sophisticated or AI tools that can rely on that. Okay, so my, let's say, key message is that we are working on a, let's say, complementary system of reanalysis extended quite a lot in the past with a very large ensemble, of course, limited the resolution. So, for instance, what was discussed by Jim about the impact of eddy induced flux is not visible in this. But for a large-scale signal, I think it's an interesting complementary approach compared to the, let's say, more recent and the deterministic reanalysis. And this was the last, so thank you.
Thank you, Andrea. Any questions in the room? Or the other room? No. But that was really interesting. And maybe we can also discuss later, just to stick to the agenda. Thank you very much. And we can move to Eric de Boissesson. Who is still alive after crossing the room. Thank you.
So good afternoon, everyone. I'm Eric de Boissesson, working at ECMWF on ocean reanalysis. So today I'm going to talk about mainly the challenges that come with atmospheric forcing and CIS data assimilation for ocean reanalysis. So when you're into producing ocean reanalysis and CIS reanalysis as well, you're always dealing with inputting new observation, new input data sets in general, and also continuously developing the model and the DA system. So here I will only focus on two important aspects that have impacted us during the production of both ORISE 5 and ORISE 6. So first is the transition from the ERA interim atmospheric forcing to the ERA 5. And then I will focus on the new multi-category CIS model, CIS cube, that replaced the single category LIM2 that was used in ORISE 5. So there I will mainly focus on data assimilation challenges. Okay, so first let's talk about ERA interim versus ERA 5. So first, when we started working with ERA 5, we just compared ERA 5 with ERA interim, and so here I will show only a few examples. So actually these slides are from people from Mercator Ocean. So they compare the radiation from ERA 5 into the ocean, and you see that the difference between ERA interim and ERA 5 is quite substantial. Okay, so the colors, they are not great, but anyway, on the bottom plot, you can see that if you run an ocean with both ERA 5 and ERA interim and you compare them so that there is no data assimilation, there is quite an impact. So the SST of the ocean is much colder when you use ERA 5 versus ERA interim. Then if you look at the fit to observation, so it's the bottom plots. So here I've plotted the differences in fit to observation when running an ocean model forced by ERA 5 versus one forced by ERA interim. Again, no data assimilation. And there you see that if the colors are red, your fit is worse. So initially, like just looking at the ocean, no DA, the ocean was worse when using ERA 5 versus ERA interim. Then we looked at precipitation, and so you can see here on the top left that ERA 5 is much drier than ERA interim in the tropical band. And this was due to a modification of the convection scheme. And this had a direct impact on the sea surface salinity. So it's the top right plot. You could see it was much saltier in the tropics. And in terms of fit to observation, again, it's ERA 5 versus ERA interim in ocean-only runs. And you can see that the impact was mostly positive. So blue colors means a better fit. Then there were also other issues with precipitation that was mainly highlighted in the work from the hydrological people in ECMWF, so that they noticed like there was a strong wet bias in the southeast of Asia and over the maritime continent. And so they noticed it in the hydrological model. And then when we had this project Bronco, where we plugged the GLOFASS reanalysis into the ocean, we could see that the wet bias transferred to the ocean. There was actually quite a strong fresh bias in over the maritime continent area. Then there are other kinds of problems that were linked to ERA 5, and there was something linked to very strong wind events. So if you look at the analyzed 10-meter winds, they can become really, really strong, like unrealistic values over 300 meters per second sometimes, and it's happening in like very particular locations. So, and this is linked to, at least that's what the DA people say, that it's linked to instabilities in the analysis method at the end of the assimilation window. So the fix they put in ERA 5 is to replace, so it's to change the processing of the analysis winds. So when you are over 50 meters per second, you switch to this fix. So I can explain in more details if you want to know more, but you can also maybe ask Answer Box tomorrow. It will maybe have more detailed answer than me. So this was another challenge that came with the transition to ERA 5. So yeah, the lessons we've learned is that you need to be really careful, and you need to monitor constantly what's happening when you change your forcings. So you need to first monitor the response of the model, then what's the DA is doing, and etc. Then you could also look into like correcting the fluxes yourself. That's something we didn't really do, apart from the winds, the strong winds, and but it's an option, but it takes a lot of time. So in the case of ERA 5, so that's what we're using on for ORISE 5 and for the production of ORISE 6. And so the latest validated version is supposed to be always available on the CDS, so the climate data store. Okay, so that's it for the atmospheric forcing part. Now I will switch to the sea ice modeling and data assimilation in a multi-category setup. So for ORISE 5, what we used, it was a LIM2, so it's this plot. So basically you've got, in a grid point, you've got a single category of concentration. So one layer of snow and 2 layers of sea ice. And what we are using now is sea ice cube, which is a multi-category model. So you've got several categories of concentration, still 1 layer of snow, and then like 4 thermal layers of sea ice. So first we look at the sea ice concentration bias in LIM2 and sea ice cube, again, in ocean-only simulation. And when you look at the biases against the Ostia sea ice concentration, you see that they are very different. So even though like sea ice cube is able to represent much more processes than LIM2, is much more complex, but so it may be able to let's say, simulate better what's happening, but it's also much more challenging to constrain. So now I will mainly focus on these challenges, at least a few of them. Okay, so when we assimilate sea ice concentration data in our system, which is using a 3D VAR FCAT system, we've got a sea ice increment in a green box, and the first challenge is how to distribute this single increment into among the different thickness category we've got in sea ice cube. Then there is also the aspect of introducing a thermodynamic balance between sea ice and ocean state variable. Then there is another thing. So like when you've got an increment over a nice free area, how are you dealing with that? And then the last point I will look at is the interaction between sea ice increment and ice advection. So this is a list of the prognostic variable you've got in LIM2 and sea ice cube. So you see that there is a huge difference. So you've got only a few variables in LIM2, while you've got like over 50 variables in sea ice cube to look at, to take into account when you're doing a sea ice data assimilation. So increased complexity. One sea ice concentration increment will impact many more variables. So yeah, like the idea, so when we got the sea ice concentration increment, how to deal with the distribution. So the idea we thought was the most consistent was to keep the sea ice state as close as possible to your background. So you minimize the changes in the thickness due to the sea ice concentration observation. Then when you've got sea ice concentration increment over ice-free area, you need to make assumption on how this sea ice looks like what is its temperature, what is its salinity, what's the thickness distribution, etc. So there are a lot of assumptions to make. Then there is another aspect is how the sea ice increment impacts the ocean around it. So what we did here is that the ice induced temperature increment, they are implemented as a post-processing to NIMOVA increment. So you've got an increment from your in situ data in the ocean. And then what we do is, so that's this equation here. So you add to your temperature increment an increment linked to the sea ice concentration and the sea ice concentration increment. So the function here is like a function of depth. So how deep your ice increment is affecting the temperature. And then here you've got some tests we've made using different of these alpha values. And so you need to look at the bottom of the plot showing that so 100% is when you compare to a control. So if you are better than the control, basically it says that without this, you're worse than when you're using this. So in all the experiments we make. So it shows that using this scheme has a positive impact on the ocean. And there is, so here is it's in terms of analysis standard deviation, and here it's in terms of background. So it shows you that if the background has some memory of the previous window, so the impact is carried forward into the data assimilation through the data assimilation windows. Okay, the last point I'm going to address is the link between the sea ice increments and the ice advection. So in the sea ice cube, the ice advection scheme is based on conservation of the first and second order of tracers. So applying an assimilation increment is by definition modifying the zeroth order. So you're modifying the underlying field of the advection scheme. So if you want to conserve the first and second order of the tracers, but you're modifying the basis of your field, then it's creating some funny features in the analysis field. So you see a lot of dotted patterns that are spurious signals. So in the end, what we chose to do is to modify the advection scheme. So we recompute the gradients after the increments instead of conserving the initial values. So yeah, okay, so this is what we got at the end of the day. So here we compare the fit to sea ice observation, sea ice concentration observation, and sea ice extent between the ORISE-6 system that is using CIS-Cube versus the ORISE-5 that is using LIM2. So here is the RMS error in terms of TI's concentration with respect to Ostia 2. And you see it's mostly positive impact. So blue colors, again, is an improvement. It's a reduction of the RMS error. And there you see a time series of the CI sextant in ORISE-5 in red, ORISE-6 in green that we compare with data from the NSIDC. And you can see that ORISE-6 in green is closer to NSIDC. And in the Antarctic, actually, it's correcting one spurious signal we got in 86 in ORISE-5. So yeah, it's more consistent also over time. Then to conclude, so there are other challenge for variational DA, especially for CI's concentration, is how we specify the cross-category terms in the background error covariance matrix. So far, we just didn't address this problem. We did this post-processing that I showed before. So there are options like implementing a diffusion operator or balance transform. So learning from experiences from people who are working on that using ENKF techniques. So this development are also expected to bring sensitivity to new types of observations, such as CS thickness. So that's the next things the people at ECMWF who are working on that will explore. Okay, thank you very much. Do you have any questions?
Thank you very much, Eric. We have time for a couple of questions, maybe. Gilles, do you want to make it?
You mentioned, Eric, you mentioned that putting the increment at the zero order make a noise because we are not you are not transporting this information with the vector scheme, but we did the same with the previous CIS model. Do you think we have this kind of noisy pattern actually by assimilating the CIS concentration?
Well, actually, I don't know, so I should ask my colleagues. Well, at least I think we never noticed it because we noticed it actually a bit by chance when looking at impacts on forecasts. So that's where, like, the fact that there were these dots all over the places, they impacted the scores in the atmosphere. So that's where we noted this. I'm not sure they looked at LIM2, but I guess if they didn't see anything weird in the previous system, probably it was not there. At least that's my assumption.
Okay, because we did see that when we assimilate the CIS thickness with LIM2.
Okay.
So we didn't really understand that. And I think we are at the same phase of you trying to implement multivariate data simulation with CIS concentration and CIS thickness. And we should discuss on that, create a group beyond all the people producing this analysis in the future.
Thank you.
Thank you. Thank you, Eric. Maybe we can move. Now it's 3, and it's time for a couple of online presentations. So we start with Joanna Slavinska. Are you with us, Joanna? Are you here? And the other speaker, online speaker, is Gianpierro Cossarini. Gianpierro is here. Nice to see you.
Hi, good afternoon, everyone.
It's not your turn, but Joanna is not here, so we're we may start with you. What do you think?
Okay, yeah, I take the floor.
Or we take time for other questions. I don't know if there are other questions in the audience, or no. Okay, let's go to. Yes, yes, yeah. Okay, so Gianpierro, if you're ready, we're happy to hear you.
Okay, so can you see my screen? Can you hear me well?
Yes.
Okay, so good afternoon, everyone. I'm Gianpierro Cossarini from OGS in Italy. I'm part of the team of reanalysis, biogeochemical reanalysis in the Mediterranean Sea. I would like to thanks and to acknowledge all the contributor of this presentation from OGS and from CMCC for the physical component of Mediterranean reanalysis, and in particular to Valeria Di Biagio. She couldn't come to Toulouse, so you have me presenting online. What I'm going to tell you this afternoon is some highlights from the biogeochemical reanalysis in the Mediterranean Sea. I would like to focus on uncertainty analysis of the primary production, which is a key process in the ecosystem, and to look at the processes that control primary production and how we can assess their uncertainties. So a very quick view of the biogeochemical model or biogeochemical system, I would say, because usually biogeochemical, as Annette presented this morning, is composed by a physical model, which is in this case NEMO, and a biogeochemical model, which is the BFM for the Mediterranean. Is a quite a complex model with more than 50 variables and 9 plankton functional types. The two are coupled in the way that the physical model provide the daily 3D fields of temperature, salinity, currents, and vertical diffusivity to the biogeochemical one. Other reanalyses are performed, you see this morning, through online coupling between physical and biogeochemical models. The two models share the same bathymetry, so the same resolution, in this case 1/24 degree, and same levels, same atmospheric forcing, initial condition from sea data net or remote net, and the same forcing, land force in terms of rivers runoff and river nutrients discharges. Physical component has a variational scheme assimilating temperature and salinity profile and sea level anomaly, while the biogeochemical, which act independently, assimilates satellite chlorophyll. One important thing that I would like to mention regarding biogeochemical reanalysis is that they are used for multiple purposes. So they are used for assessing different aspects of the ocean health and monitoring different processes in the ocean. For example, the Mediterranean one has been used for assessing the carbon cycle, is the base for the use of a spatial distribution model to assess the distribution of fishes or probability of habitats for fishes. The oxygenation, and one of most important, I would like to say, process in the ecosystem is primary production. So, which is the basis of the ecosystem food web and the engine of the biological carbon pump for the carbon sequestration. So I'm going to show some elements of the primary production and how the primary production can be assessed and its uncertainty. We saw this morning in the presentation of Annette that the primary production was in the yellow block of variable that was the variable that are less assessed, I mean, in terms of capacity of providing uncertainties estimation for the product. So in the case of Mediterranean Sea, here is the map of integrated annual value of primary production, with the western part more productive than the eastern part. But what is more important is that there is an important vertical component for primary production. Mediterranean Sea is a oligotrophic quasi-permanent stratified sea, with the western part that are subjected to winter convection or mixing that inject nutrients in the euphotic layer, and the occurrence of winter surface bloom that you can see here. I guess you can see my mouse. While during the rest of the year, especially in summer, the production is mostly related to the whole water column down to the deep chlorophyll maximum. So keep in mind these two particular. We can assess the quality or the uncertainty of the primary production, looking at what is available in terms of observation or estimations. There are very few in situ observation, very few experiments looking at the primary productivity in water. Satellite estimates provide other information, and so we can have only a qualitative comparison between what is simulated by the model on the right and the satellite or the in situ estimation on the left and in the numbers. We can look at the vertical dimension of the primary production. In this case, we can use oxygen-derived measurements using they use oxygen chamber to measure production of oxygen and consumption of oxygen due to the community respiration. On the right, on the left, you have typical profile in different seasons in different regions, with a decrease in from surface to the bottom of the euphotic layer of the productivity. And on the right, just a table showing the very few data available that allow us just to say that the model is good, at least in capturing the range of variability for different layers in the different regions. So what we can do to assess the quality or the uncertainty of a process like primary production, which is really important for ocean health. We can look at some of the processes that control the productivity of the sea. So the first one can be the winter fertilization, which means the injection of nutrients from the deeper layer to the surface in winter that trigger the subsequent productivity in the upper layer. Mediterranean is a very particular sea because it's semi-enclosed, so the floats, the algal floats that are inside can stay there. So we have a quite high density of floats that can be used to assess some properties of the sea. In this case, in the blue boxes, you see the fingerprint of the injection of nutrients at surface. So we can investigate this looking at some specific metrics, so the value of a surface of nitrates or the chlorophyll, the nitric line, so the depth at which concentration of nitrate is equal to a threshold, in this case 2 millimole per cubic meter, and in dot you have the floats, in blue you have the model. So we can make some statistics and looking at the spatial temporal capacity of the model to reproduce the movement of nutrients at surface. A second good example of how to use floats is looking at the summer period, where when the activity of phytoplankton is mostly located in the layer that is called a deep chlorophyll maximum, here with this highlighted by this higher concentration in the subsurface layer. So we can build some metrics specific to the to look at this process. So the concentration, the highest the concentration of chlorophyll, the deep chlorophyll maximum layer, or the depth of this layer here on the bottom. And again, thanks to the fact that there are many floats in the Mediterranean Sea, we can perform statistics which represents a benchmark, a basis for the future developments of the model. So looking at which direction we can take for improving the next generation of reanalysis, and looking at the vertical aspect of the productivity of the sea. First of all, we work with the physical component, and at CMCC they are developing the new physical reanalysis. They tested some improvements related to the quality and quantity of observation assimilated. And here in this plots, you have the comparison of the root mean square difference of the old reanalysis with the new system for simulation of 5-year simulation, and at different layers, and the root mean square difference decrease from the blue to the red, which means that the new version of the model, the new version of the reanalysis, the physical reanalysis, will be able to improve the representation of the thermocline and the density, vertical density gradient, which should imply a better representation of the mixing and on the injection of nutrients from the bottom to the photic layer. Even if, also reminded by Annette this morning, assimilation of physical improve the physics, but it's not straightforward. That has a positive impact on biogeochemistry. So this is an aspect that has to be investigated. A second major direction for improving the capacity of the model to reproduce the vertical dimension of productivity is look at the new developments on the optics, so including a biooptical model in the biogeochemical system. BFM now has a 3-stream light model formulation, which includes a split sheet formulation for absorption and scattering of phytoplankton and other optical components. And this is in use in the forecasted near real-time system, which showed a decrease of the uncertainty for those metrics that I showed before. So the depth of the chlorophyll maximum and the value of chlorophyll integrated in the photic layer. And as a last direction that can be thought to improve productivity, the way we describe productivity in the model is to include in the reanalysis the assimilation of biogeochemical Argo profile together with the assimilation of ocean color, which is in place right now. Here is an example taken from the near real-time forecasting system, the sequence of the versions of the biogeochemical model with the inclusion of the assimilation of chlorophyll, nitrate, and oxygen in different years, with the darkest color are the oldest version, and you have the reduction of the uncertainty of the root mean square difference, especially in the subsurface layer in the newer version of the system. So just to give some key message, the biogeochemical reanalysis is used for several objectives in looking at the ocean health, monitoring different processes. And since there is a lack of observation for some, like primary production of these processes, we should also look at how to assess uncertainty of those dynamics that control the indicator that we would like to produce and we would like that user are confident to use. What we are going to do in the next reanalysis is to work with the new physics, a new biogeochemical model, and inclusion of the vertical profiles from biogeochemical Argo. Yeah, and that's all from my side. Thank you. And if you have any question, I'm here, or you can contact Valeria and me by email.
Okay, thank you very much, Gianpierro. There was a large applause that you didn't hear, but you were applauded by the audience here in the room. Any questions? Okay. Yes, yeah.
Hey, yeah, nice presentation. I was wondering whether if you have a sense of the best input for the radiative transfer model, I guess you need, a sort of detailed representation of the light incoming. Is that an issue, or do you have an advice or thought on that?
We started using the OASI model, adapted for the specificity of the Mediterranean. There are some peculiarity that has to be considered. The aerosol, and so we use ECMWF data for forcing the OASI model for the radiative transfer component in the atmosphere.
Okay, thank you very much. So now we have some time for another question, maybe? No. Okay. And so if Joanna is not here, no, she has not shown up. So thank you very much, Gianpierro. And now we are going to move to a discussion session. So we can take, you can come with me if you want.
We need to see the Slido poll, maybe.
Yeah.
So we want to see the poll now?
What we propose is that we use the Slido poll answers to open the discussion, and can be a large discussion within this room based on the feedback we have from people who answer the Slido poll. And so, Vincent, if you want to show it, we have. While we are here, we have very few questions from the Slido questions today, this afternoon. There was one question for Joao, but we already asked. Okay, yeah, okay.
I don't have further questions.
No, I think it's okay. Okay, so this one is going to be difficult to analyze right now. So maybe we can leave that for later. The feedbacks on the strengths and weaknesses, because it was open text. And maybe we can move to the famous shopping list.
Yeah.
Directly. Okay. So we asked people to choose between categories, and so for the domain, the resolution, the period, and
coupling,
the type of coupling between components. And so we have 61% asking for global, which means that we have 40% asking for regional. We will see what they ask for. For the resolution,
we have asked either deterministic but higher resolution, or Ensemble a little bit lower resolution. I think people prefer to have the.
So okay, so the deterministic high resolution comes first. Then the period is extended to the 1950s. Okay, and so the regional domain is also asked for sure, and then coupling, ocean, ice, atmosphere. Wow. And also we have a 40% for probabilistic with lower resolution. Okay, the period, altimetry, era.
40%.
Okay. And so the need for a long period and longer period is the first thing coming out of the poll. Yeah. With the high resolution.
With high resolution, and they want both high resolution and also long-term period.
So this couple is not the right one, okay?
Exactly.
Because this is not at all the plan. The plan is to have maybe high resolution but on a shorter period, and lower resolution on a longer period. So we can have both products, but that would be two products, obviously.
But also global. So if we plus the top 3 together, we're not able to have actually. Yeah.
So, but that confirms that there's a need for each one of these.
Yeah.
And we need to develop these, maybe not, and it will not be one product only.
Yeah, multiple, yeah.
Was there another question after? Oh, so this is 100% people said, yes, we want an intercomparison exercise. So that's that was, you know, how do we call that?
Yeah, we have to do it.
This was a very closed question. But no surprise, everybody agrees that it's a good idea. Okay.
We will keep it alive, maybe this poll.
Yes, we can keep it alive
until
the
the end of the
night.
day. Yeah.
And then there's another poll for the following session on the link between coupled models, coupled reanalyses, and ocean reanalyses for the following session. Okay.
On the climate community, yes.
Okay. So
we also have some
suggestion. If no, what do you suggest? So there was no, but we have suggestions to support new maritime research with regional maritime coordination and union to work together and enhance maritime security. Okay. So that's a new project from someone. Yes, but it should be tailored to different needs. Okay, so
Yeah,
that's what we need to do is to extend the intercomparison exercises we did before to new, maybe to regional processes studies and to specific needs that were not taken into account before because we were looking at integrated quantities for climate use, trends, etc. And now we can move to other quantities like surface currents and things that have for other needs or other reanalysis users that, okay. Come speak in the mic. Yes, before starting.
Yeah, I think we need the outcome from yesterday to perform some classification of depending on the need and what we are able to process also, something like that. Maybe a table or some will be very useful to be clear.
Heavy metal. So we are doing heavy metal. Okay. No, it's not. Okay. So, but of course, we have to take into account all the needs, and this will be explored further. And what we are aiming at is to write a white paper after this workshop with your contributions, and issue priorities, and order all of this input into something that can be the start for the next intercomparison. Okay.
Any comments from the audience based on the feedback?
So I recently participated, about 10 years ago, I participated in a model intercomparison project called IMARNet in the UK. And it was a comparison of several different marine biogeochemistry models. And the question I have for the room is, how do you stop reanalysis comparison turning into like a mudslinging competition or a beauty contest?
Well, in the past, we have been using the strength of having several estimates to compute an ensemble mean, ensemble median, and see how do we outperform any individual member using this ensemble. So that's the first point. Now it's also that the models or the systems, as has been said previously, they are never the best everywhere and at every moment. There's always one performing better in one area and the other performing better in another area or for another variable. And that's it. We can also illustrate this if we look at very different processes, well, a wide range of needs. If someone wants to complement.
Oh, me?
Oh, yes. Jim is invited to come.
Okay. Well, actually, if I were to just follow that, I guess one question I have is if you're going to do these intercomparison projects, are there certain regions that you'd like to have as focus. I can understand you do the global region, but I can also see that the Arctic and in particular the Southern Ocean might be worth kind of focusing on. So I'm curious to see if other people agree with that.
Yeah.
I'll just add something that I think you'll like, Jim, which is that it'd be great if we had more of an insight into data assimilation increments from this intercomparison. So if every center can save those, make sure that we can sort of incorporate them in the. Yes, exactly.
And we know we need to use them too for AI, right?
Right.
So yeah.
And in terms of quantifications of error for the budget and so on, I think it'd be something we didn't really do in the previous round of this intercomparison as much as we should have maybe. So I think that would be one thing I would stress.
Yeah, there were some efforts, but not for every reanalysis, maybe. So generalize this. Yeah. There was a question also from Slido, but maybe we can go on this. Yosuke, yes.
What is the question?
So basically, if we do perform the intercomparison project, what is your?
Yeah, I think intercomparison is it's best timing to start intercomparison because all IP is started I think 2011 and it finished to 2017. So it's about 10 years, and now we are doing United Nations Ocean Decade. So it's we have motivation to collaborate. So, but on the other hand, we have many activities related to UN Decade and also ocean predictors. So good collaboration or good coordination of those activity is necessary. So without coordination, we have too many activities. So yeah, we need some coordination. So
thank you.
Agreed.
Yeah, the regional reanalysis. Any idea?
Yeah, I think each regional MFC can be included in their specific domain in like a subchapter of this intercomparison, like Mediterranean Sea or the Baltic Sea. Arctic probably will be already there. So yeah, definitely can be a plus. Also include regional systems which are higher resolution compared to the global ones. So it can be beneficial also to have the regional systems on this intercomparison.
Biogeochemistry.
Yeah, I mean, it's super interesting, but would be a subset. And also, I think sometimes the difficulty with this model into comparisons is you see all these differences, right? But explaining them, why do these occur? So maybe, but maybe that's too ambitious. And also with the biochemistry, we have so many different models. But yeah, but maybe for the biochemistry, it's important to kind of frame it so that we can have a clean intercomparison put on some variables where we have many observations, and then just forget about the rest. Otherwise, it's too much work.
We can precondition the clustering. But yeah, Gilles wants to say something.
In fact, if we do this in comparison, we could use a maximum of observation also, because there is a lot of spread of observation, as I mentioned this morning. For example, for the CS concentration, it exists 30 algorithms to find for the retrieval of CS concentration. So can imagine the spread among the observation. We get used to have 3 different kind of CS concentration from satellite in the polar ORIP. And just these 3, we have a lot of spread, in fact, and especially in the summer times. So I mean, if we do this intercomparison, we should gather as much as we can the observation, because like that we'll have the spread of the observation. They can provide us the uncertainties of the observation we could afford for the assimilation, for example, and the evaluation. I think it's very important. especially for the CI, because there was a lot of data now on the market, I would say, for the CI thickness, for the snow volume, for the drift. And if we don't take into account these errors, I think we go we don't consider the problem. Yeah.
And moreover, I've seen in the Slido there's a question about also how can we as a community do to have an impact on climate change policy? What will the reanalysis look like in 2040? So if we focus also on polar areas, I think it's also a way to really, if we want to make progress in that area, and as you said, bring more insights on the uncertainties, etc. It's very useful in that context. Yes, Ronan. The next
Yeah, maybe one comment regarding the intercomparison exercise. Would be interesting if it could account for the application of deep learning or learning-based schemes that may require additional or we may have to consider additional requirements, especially the ability to learn things. And and that's based on our experience for the ECCO mapping, where initially that was not designed for learning techniques, and then it may not have been optimal. So yeah, maybe.
So will you help us with this?
Yeah, sure.
Julien and you.
yeah, we discussed that somehow with Jan yesterday, so not sure if interest.
Thank you. Yeah, are there any questions from you, Gianpierro, for instance, or remote? You are our remote speaker of the day. No. Yes.
Yeah, sorry, I couldn't find the mic. Yeah, I would like just to mention again issue of intercomparison for biogeochemistry has a net highlighted. Biogeochemical models are really diverse, one from each other, and in Seamless, which is a project that put together all the Copernicus model in the same framework, we were able to analyze some behavior of different models in a single location. So for intercomparison, I would suggest to the needs of building some framework for comparing biogeochemistry and biogeochemical models. Yeah, that can be useful also to for developer to assess the meaning of different processes that are coded in with different formulation in different models.
No.
For the waves, there is a very maybe interesting and ongoing project is to compare overlapping area in terms of wave reanalysis in the frame of the Copernicus, and also to try to include the wave risk, for example, for people working on the wave climate projections. This is could be interesting in terms of I think the wave risk is the only wave reanalysis including the current, comparing to the other product. I think that it should be this should be very interesting in terms of variability and wave climate projection. Comparison also with ERA 5 and ongoing work on the next release of ERA 6. This will be very
way to progress, I think. And also there is yeah, Joe, you want to comment?
Thank you. Following what the same framework, I think the project that I presented before, it's also looking into comparing the different regional wave climate projections, including Europe, where we have a high availability of these different data sets conducted in a different way. And I think that's a very valuable task to actually do that for the reanalysis for the current period, because we need to understand more where those differences sit within the context of the projections as well. So I think it's a very nice task and it's going to fit really well. I think we can see in Europe, especially, there is a more progress towards collaboration in putting these products all together and into comparison, which would be nice to see in other regions of the world. But as far as I know, there is a high availability of products in Europe right now, and it should be explored.
It's not very clear to me yet if you are planning to coordinate a intercomparison experiment using all the reanalysis systems, or you would like to compare the existing reanalyses. But Ronan's comment on the deep learning schemes and design the new experiments for the learning scheme, considering the requirements for the learning scheme, reminded me the question of Julien Brajard that he made yesterday, asking if the length of the reanalysis that we have is suitable to learn from the reanalysis. So maybe if the intercomparison will be redone using the existing systems, we could also try to extend the reanalysis back in time, maybe to approach more to the climate scales than only remain in the satellite era. That is definitely some need, as I presented this morning, from the regional systems, especially for the boundary conditions and so on, or initialization, also another requirement. So if this idea of intercomparison will be coordinated to perform new experiments, this aspect can be also taken into account. Maybe that can be very useful for most of the users.
I fully agree, because especially for this, I think it's not yet clear the trade-off between observational sampling, that of course is needed to have reliable data set of analysis increment to learn from, and temporal extension. I think it's not really clear at this point, and we probably need to play with Ensemble and longer reanalysis and understand this. The other comment, maybe in addition to what Gael said about analysis increments importance, I think also surface currents and mesoscale activity were not really investigated in the previous round of intercomparison, and I see now there are products that are increasing the resolution, increasing complexity of data assimilation, and I think in this specific regards of mesoscale activity, we can learn more, because of course it's a combination of resolution, strategy of assimilation of altimetry, and many other issues. So it's at the same time there are less reanalysis than before, so it will be easier, I think. I mean, there are just the number decreased for some reason.
Yeah, maybe we can go on discussing at the coffee break for people who are here. And people online, we see you back at 4 o'clock. Thank you very much, Gianpierro. Thank you very much, online audience. And we will be back at 4 or 4:30. Yeah, 4:30. This was a round table. It was a very big round table. Improvised. 4:30. So you 4:30. So you have time. You have free time right now. Thank you.
Okay, so my talk is probably going to be different from a lot of the other talks we've seen this week, mostly because most of the stuff I know about reanalysis I learned in the last 2 days. So it's a new field for me. My actual background is I'm a marine ecosystem modeler, and I work on Earth system models, particularly the United Kingdom Earth system model, UK ESM. And what I've been doing is I've been working on the operational monitoring of the marine component of that. And I've also been working on some scientific evaluation software called ECMWF tool, which is used to analyze CMIP data. So I'll get into what all those acronyms mean for those that don't know them yet. But my general interest is marine ecosystems, marine protected areas, climate change policy, and the carbon cycle. Down. So to introduce Earth system models, so we all know what an ocean model is, of course, so you're used to dealing with NEMO. Well, in Earth system models, NEMO is just the marine circulation component. We also have an atmospheric circulation component, an atmospheric chemistry, marine biogeochemistry. We have land models, we have sea ice models, we have, did I say marine biogeochemistry? We have dynamic vegetation models on the land. So it's actually lots of models all coupled together. So that's where the coupled part of CMIP 6 comes from. So the C is coupled model into comparison project. And in order to participate in CMIP, there's a whole set of simulations that are required and various other sort of standardization requirements. So they're called the DEC simulations. And that includes things like a pre-industrial control. There's a historical run. There's a 1% gradual CO2 rise. And then there's a rapid 4 times CO2 rise. So those are different experiments that are kind of required. They're the entry card to participate in CMIP 6. There's also some very specific data format requirements that I'll get into in a bit. And there's model quality requirements. And the big one being you can have at most 0.1 degrees of drift in your surface temperature per century. So you have to run it for a century to find out how it's going. There's also a similar, you have to have a very low century mean of your SE CO2 flux. Down. Okay, so the tool that we use to compare Earth system models is ECMWF tool. This is a Python-based model into comparison tool. It's built to be extremely modular. So it takes the CMIP 6 data, and then there's this, I don't know if you can see the yellow boxes, but each one is a modular function that applies some operation to your model data. So this could be extracting the surface layer, or a transect, or looking at a specific region, or applying some kind of regridding, or potentially some time operation. So do an annual mean or a decadal climatology, something like that. So there's lots of different modular functions. And you tell ESMVal tool which ones you want in a YAML file. So it's very straightforward to use and write a recipe. And once it does all this pre-processing, it gives you like a set of nice, neat netcdf files that you can then run a diagnostic over and perform like science, basically. So I was one of the developers of ESMVal tool. With my focus was on the ocean development part. And I was kind of brought in as a hired gun on IPCC AR6, so the 6th assessment report. And I contributed to like these plots and a few others. So I worked on things like ocean heat content, the AMOC, thermosteric versus halosteric sea level trends, different transects, and trends in surface salinity. So quite a wide range of physical things for someone who's actually a marine biogeochemistry modeler. So it's just, I was the guy that knew how to use the software, so I turned the handle more than I performed the interesting bits of science. But one thing you will notice is there's not a whole lot of reanalysis in any of this. So that's kind of the first point that I'd like to make, is that we could probably do with more. So in the future, I think I will endeavor to include more reanalysis in my work. Just, so there, I've said it. But in CMIP, there's two general uses of reanalysis data. And the first one being a comparison against like a ground truth observations, or some of the best data that we have. And then the other one will be using, sorry, I added too many bullet points and now it's all struggling. So we're doing scientific evaluation, and then we're also doing benchmarking while we're running our models. This isn't working. Oh, there we go. Okay. So one of the pieces of software that we use is BGCVal, but each modeling group will use their own software. And there's probably, well, there's dozens, if not, I think 50 or 60 different models in CMIP 6. So each one will make their own decisions on how they do the monitoring, but we're trying to get as many people as possible to use ESMVal tool for the scientific evaluation of the CMIP 6 data. There's also some of the other stuff that people have talked about, like boundary conditions and things, but obviously you know more about that than I do, so I'll just skip over that. I'd also like to talk about a case study that we've used, that we've done recently with Ascension Island. So Ascension Island is a small island in the equatorial Atlantic, and in 2019 it was declared a marine protected area, and it's one of the top 10 largest marine protected areas in the world. It's completely 440,000 square kilometers, no fish, no mining. Well, local artisanal people are allowed to fish, but it's very small scale and recreational at best. And there's only 800 people that live on the island. So it's not a huge environmental impact. And we actually did the first projection of the MPA since it was created. This was actually commissioned by the Ascension Island government, which is part of the UK Overseas Territory. And yeah, so what we did, I'm guessing you probably can't see the words here, but we did an analysis of the temperature, salinity, the currents, specifically the Atlantic equatorial undercurrent. We looked at the mixed layer depth, pH, oxygen, phosphate, nitrate, chlorophyll, and primary production. And so this is kind of how the different trends look. And most of the time, yeah, okay, well, it was most of the time, the mean is all in agreement with all 4 scenarios. Okay, thank you. And so what was I going to say? Yeah, the model mean. So this is the recent past, so the year 2000 to 2010 versus the mid-century future, 2040 to 2050. And the black line is no change. And then it shows you whether it's rising or falling. And sometimes the pH is the clearest signal, where the scenarios with the strongest climate change have the biggest effect. But without getting into too much detail into what this is about, we basically performed, oh yeah, okay, so the manuscript was submitted and hopefully is going to be accepted pretty soon. There we go. So what we did was effectively, we generated this multimodal comparison for each of the variables that I just mentioned, with this one being temperature. So the different colors are the scenarios, and the black line is the observational data. And I'll get into that in a sec. So where the observations come into play in this are the purple boxes that I just drew there. So temperature, we have a climatology, we have the depth profile for the time period, and we have a surface plot. So with these like analyses, that tells us quite a lot of information about what's going to happen within the marine protected area. And we produced 9 of these plots for each of the different fields that I mentioned. Oh yeah, so I just said that. So, and I just said that. So the observations that we used. So here we use the ERA interim sea surface temperature, but we also use primarily World Ocean Atlas datasets. We used GLODAP, we used CCIOC, we used MODIS, and we used the Tropical Atlantic Observation System for the equatorial currents. So those are the observational datasets we used for this study. So in this case, might be a little controversial, but CMIP6 models are pretty coarse resolution, about 1 degree. So it's, you guys are doing like 1/12 of a degree, 1/24 of a degree. Like for our use case, like 1 degree is more than enough to validate huge chunks of our models. The historical period that we used started in 1850 and runs to 2015. So, we don't urgently need to validate our historical model with up-to-date, the most recent observations. And even CMIP7, which is still in preparation now, and we haven't got the formalized outline of what we're doing, it's looking like the historical period will run until 2020, and then the future will start in 2020. So once again, that's not, and that will be we'll be making those models in 2024, 2025. So it once again won't need like the most recent data. What we will be missing is the first 100 years. So the other point that's not important to make here is that the historical period starts at an arbitrary point in the climate phase. So that means that the forcing that we use is from atmospheric CO2, but we generally let most of the aspects of the ocean and the atmosphere just run without trying to tie it to a specific time series, apart from volcanoes. And so that means that the model year 1995 isn't going to look like the real year 1995. It could be an entirely different part of the El Nino and what have you. So with that in mind, we don't necessarily need hourly data to validate the models. Monthly is generally what I would use. Some people use daily, but there's a lot of work being done with annual and even decadal means, which is why using something like the World Ocean Atlas datasets is perfectly sufficient. It's 1 degree, it's monthly, it's annual, and it's a climatology. And that's what we can use to sort of demonstrate that our models are in the right ballpark. Now, this is my personal experience, and there's a lot of people in CMIP6. So your mileage may vary. You might find that some people really need very specific things, but this is just what I found. So there's also, we mentioned this briefly in the discussion before just now, but there's the expensive problem with CMIP6 models, and this is what we are facing now in the Terra Firma project as we begin to spin up our model for CMIP7 for the upcoming experiment. So as you all know, subducted water can take thousands of years before it comes back up to the surface. And therefore, the models need to run for thousands of years in order to fully equilibrate. So that means that if your model isn't fully spun up, then you could be outgassing CO2 or absorbing CO2 from the atmosphere, so that when you start the pre-industrial period, you're already moving and you have a trend, which would ruin the entire carbon cycle of your model, making it not that useful for a lot of the key analyses that form like climate change policy decisions and things. So you really have to be fully spun up and fully at equilibrium before you can even start the historical period. And then once you do that, you need to run at least 1 historical simulation before you can even get to the observational period. So it's like Sisyphus pushing his rock up the mountain. Like you could do all this work, and then you get to the top and like, oh, it's wrong. Oh, back to the beginning. What are you going to do about it? Like this, if you've spun up and tuned your model and run it for 5,000 years, you know, that's a lot of computational time. And that's one of the reasons why in CMIP 6, you may have heard there was this issue with sensitivity. Like some of the models were very sensitive and the target was very different. And it's because it is so expensive to even get to the start of the simulation. So this is possibly an impossible or controversial idea, but if we had a pre-industrial like target that we could aim for, that would actually make tuning and building and running up pre-industrial like a lot more easier to validate, if nothing else. So I know there's no actual data for 1850, but you know, if you could like use an AI to figure out what the temperature would look like, just dial it down a bit, or so I don't know. It's just a crazy idea. I had to say it. The next thing I was going to say, okay, but so I think what I've shown is like the needs of our community aren't necessarily more resolution or faster time step or anything, but we are actually we have more pragmatic things that would really help us use more reanalysis data. And so back to the example of the MPA, the Essential and MPA, that was a commissioned bit of research, and there was 40 days of human effort provided for that piece of work. And so, you know, we need everything to be just ready to go as soon as possible. We can't spend 6 weeks preparing the observational data set. We just need it there, and it needs to be in the right format, and we need to just trust it. So the way that we that I generally use data in ESMVal tool is via OBS4MIPS, which is a specific project that's designed to convert observational data into the CMIP format. So when I use it, this is kind of the process that I use. So I download the data, and if I don't have a direct download like path, then I have to copy it to my machine and then copy it to the cluster, which then adds an extra step of complexity. And if there's a password or a Java GUI or something, like I'm just not going to use it. I'm sorry, it's not happening. Then if there's not a tool already existing, you have to develop the tool yourself, which means spending more time writing some script to convert it to the right format. And then, you know, we check the licenses of products. And if it's something that we're allowed to rehost or reshare, we'll put it in a shared folder. And then once we've done these first 2 steps, everybody that uses the ESMVal tool can access that data. But if the license says you're not allowed to rehost it or share it, then that means no one else can do it. And we can only reshare the script. So they'll have to download it and run everything themselves. So that's another barrier to entry for using this data. Then the way that we use observationals in this format is we treat it like CMIP 6 data. We make sure it has all the same formats. And then we just put it in our ESMVal tool recipe. And then it knows how are we doing for time? 1 minute. Oh, okay. So yeah, we just want to make sure we can avoid as many pain points and barrier to entries. So this is my last slide. I won't read it all, but basically like making things standardized, making them so that the licenses mean that we can share them with our community, and making them accessible so that we don't have to go through a GUI. We can just download them and access them. And, you know, for bonus points, if you can give us the DOI and a BibTeX file for publications, that would just be amazing. Thank you so much. Yeah.
Sure. Questions? Question in the back. Okay.
Yeah. Maybe only one.
Sorry, coming from the other room. So thank you for this very nice talk. I have a question in terms of energy in the climate models, and also dense fresh water from melting processes from the climate models. I think those are 2 aspects which are, let's say, still a challenge in terms of. So I was wondering whether one could also think about discussion on how this type of communities could work together, and also linking with the observing communities to probably identify, for example, heat leakages or even losses, or also to see that maybe the reanalysis community, so maybe can comment as well more on opportunity whether we can get information from this melting and water, which maybe is also a problem in renal systems, but how we can discuss this together also with the observing system community, because it would help all the communities and also to improve the prediction.
So I can discuss this. I'm not an expert on ocean heat by any means of I'm marine biogeochemistry, but I know that there's one of the things I didn't mention within CMIP is that a lot of the time people think of CMIP as just the scenarios, so looking forward into the future. But there's actually 23 different model intercomparison projects in CMIP 6, and that will include things like a carbon cycle MIP, a paleo MIP, looking at sort of paleoclimate. It will include things like volcanoes and fish, and all of the different aspects of things that we look at may have a set of experiments, including ocean heat, that will be dedicated to studying that specific analysis in great detail. And then the modeling centers can choose to participate in them. So if you have a specific scientific aspect that you'd like to look at, it's worth finding the relevant MIP and then getting involved in that community. That'd be the advice.
Yeah. Okay, we should probably go on. Next speaker is Garric. Yeah.
Good afternoon to everyone. I'm Dario Nicoli from CSP division of CMCC in Bologna. And today I'm going to present a shade of the CMIP world, which are the decadal prediction world. So I'm going to present the decadal prediction, which is a specific aspect of the CMIP. And in particular, I'm going to present also the added value due to the initialization, in particular to the ocean initialization. So let me briefly introduce the topic. Decadal prediction, climate prediction lies at the confluence between the initial value problem and boundary value problem, and that can potentially benefit from both a realistic initial state and imposed boundary forcing. So here it is in this cartoon, we can see in blue, light blue, the historical simulation, which are the classical historical simulation initialized in 1850 with pre-industrial condition and then subjected to the historical external forcing. While decadal prediction, on the other hand, in green in the cartoon, are initialized every year, starting from 1960 to nowadays. They are 10-year long simulation. And if you focus on the right, when we refer to LIDR1, we want to say that we are considering the average of the first year of simulation, LIDR5, the fifth year, and so on. It's important to highlight that the historical simulation and the decadal prediction share the same external forcing. So the only difference is the early initialization that we made in our decadal prediction. All the data can be downloaded by the ESGF portal. But the CMCC obviously is not the only center that produces the decadal climate prediction. There are several contributing centers that provide their decadal predictions to the WMO. And the WMO every year released a draft annual to decadal climate update in which you can find the multimodal evaluation of the systems and also the multimodal forecast for the next 5 years. I want to highlight that the forecast issued in November 2020, so the forecast for 2021-2025, has indicated that, as predicted, partially the dry tendency that covered the south of Spain and partially of the south of France in these years. So now I'm going to present our system. The CMCC decadal prediction system is based on our couple model in its standard resolution. So 1 degree per 1 degree of spatial resolution. The hindcast are initialized every 1st of November, starting from 1960, as I said. And the ensemble size is now 20 members, but we are increasing up to 40 members in order to increase the signal-to-noise ratio. The protocol is outlined in CMIP 6, Decadal Climate Prediction Project, and we apply a full-field initialization strategy. So we provide a snapshot of the 1st of November of the atmosphere, the land, the ocean, and sea ice components. In particular, we can see that for the ocean and sea ice, we have used CHR reanalysis for the period 1960 to 2010, and SIGLORS in its 7th version for start dates from 2011 onwards. In particular, we have used 5 different initial conditions, free initial conditions from realization of the global ocean reanalysis, and the other 2 from linear combination of the former 3 initial condition. We provide these variables to initialize the system. For the ocean, the predicted state of temperature, salinity, and horizontal components of the ocean currents, while for the sea ice, we provide the sea ice temperature, volume, area, and snow volume. Here it is shown the anomaly correlation coefficient for the surface temperature, 2 meter temperature over land, and sea surface temperature over the ocean. We use these deterministic metrics to indicate the skill of our system. The top panels represent lead year 1, so the first year of simulation. The bottom panels represent lead year 1 to 5, so the mean of the first 5 years of simulation. On the left, we have our system, the initialized, and on the right, there is the difference between the decadal prediction and historical runs. During the first year is not so unexpected because we are very close to the initialization. We can see that the skill is quite high along the covering the global domain. In particular, over the ocean, we can see that high skill is located over the subpolar Gilles, the tropical Atlantic, and the Indian Ocean, and the Western Pacific, but in general covering the whole Pacific. While when we look at the DL 1 to 5, the bottom left panel, we can see that high values of skills covers in particular the whole North Atlantic Ocean, the tropical South Atlantic Ocean, and again the Indian Ocean and Western Pacific. The only exception in the North Atlantic is the Gulf Stream, and this is obvious because we are working with a model which has a grid of 1 degree per 1 degree, so we are not able to capture the meandric path of the Gulf Stream. But what is interesting is that if you look at the right bottom panels, the gain of skill that we have is substantially located over the subpolar gyre. And this is very important in a coupled system because most of the teleconnection that driving predictability also over land, especially over Europe, are located in that area. Here it is shown the ocean heat content integrated over 300 meter depth. And here it is shown just to see that we are consistent with the SST plots that we have just seen, just to indicate that not only the sea surface temperature is well captured, but also the upper layer of the ocean. Here it is shown the annual time series for maximum EMOC at 26.5 degrees north from the rapid array in black and our decadal prediction system. In particular, on the left, you can see the lead year 1 which is again close to the observation. So our system can mimic the EMOC variability, at least in the record of the array, of the rapid array, very well. While when we look at the LIDR 1 to 5, we can see that the EMOC is quite low. And this is not so unexpected again, because when we initialize the system with a full field strategy, the model tends to deviate toward its model attractor. And so this can cause the decrease of AMOC strength. Another important aspect for us are the climate indices. Here it is shown the AMV, the Atlantic multi-decadal variability, estimated following the formulation of Tempest shear. And looking at the right top panel, we can see the ACC for the AMV index for different LIDR ranges. It's important to highlight that the color bar ranges from 0.5 to 1. So we are able to catch the AMV index in several LIDR ranges, and the maximum is reached in this case at LIDR 410. In fact, if we look at the time series for the AMV, we can see that the red one, which is our hindcast, and the black one, which is the observation, goes closely throughout the time record, while the historical simulation is not able to catch this index. In fact, the lack of initialization doesn't allow to produce the right internal variability in the ocean. Another important index for us is the North Atlantic oscillation, which is given by the classical definition from Lee and Wong. Again, we are able to catch the ACC of the NAO index, with a quite high value of ACC, 0.58. And in fact, we can see in the time series that the red one, the decadal prediction, can follow the observation, including the increasing of the index occurred at the end of the 80s, and the following decrease occurred after the 90s. So summary, and summarizing, the decadal climate prediction benefit both initial condition and external forcing, which play a crucial role in determining the predictability of the climate system. And in this context, the ocean reanalysis is an important component. In fact, the initial state of the ocean is responsible also for the internal variability within the ocean, and in a coupled system as ours, is also responsible for the teleconnection, for instance, triggered by its interaction. So what are our needs with respect? Next. Oh, sorry. Okay. So to have a perfect ocean reanalysis to use to initialize our decadal prediction, ocean reanalysis should cover the global domain, because we run global model. It should start from 1960 or even back in time, because in the next CMIP exercise, the idea for the decadal prediction is to start from 1950, for instance. And also in our case, we had to use two different reanalyses, CHR and CGLOS, to cover the entire time record. Have enough horizontal and vertical resolution, because the future decadal prediction system will go to increase the resolution of the model itself. and also to include a consistent sea ice component, because this is essential for the North Atlantic predictability. Moreover, it would be ideal that the ocean analysis have an adequate spread among the ensemble members in order to facilitate in order to catch better and to quantify the uncertainty. And merci.
Questions?
Thank you for your talk. What do you mean by having a consistent sea ice for your decadal prediction? Do you mean if you have a consistent sea ice extent is enough? Do you need sea ice volume consistent? What do you need?
No, for instance, we have chosen the CHR analysis because they provide both the sea ice and the ocean, and they are already in equilibrium in terms also of transport, of melting and so on.
Questions? Are there online questions coming in? I haven't been checking.
Specific.
Okay.
I don't see online questions for this specific. Oh, yes. Is the signal to noise ratio in your system smaller than it should be, as it is in many other systems? Sorry. Is the signal to noise ratio in your system smaller than it should be, as it is in many other systems?
I don't know the other systems, but anyway, no. What we mean is that increasing the number of members, we can better assess the signal to noise ratio, for instance, of the precipitation, because it's very difficult for us to catch the right precipitation in our system as in the other system too.
Okay. So I hope Mike is online and asking this question, Mike Bell. So I hope the answer is okay.
I have a question. Usually, how many members do you need, for example, for the initialization for your decadal prediction experiments?
And we have here in this assessment, we have used 5 different members, 3 from the reanalysis and 2 from linear combination. The best idea would be to have as much possible members for the ocean, because the ocean driving decadal predictability substantially. So more members, more ocean members means more means that we can perturbate the system better.
Okay. How many do you have when you run the decadal prediction? Usually, how many members do you run for the decadal?
And we are reaching the 40 members.
Sorry, you have mentioned.
We are reaching 40 members, so I think that 10 members would be ideal for initializing the decadal prediction.
Okay. Thank you. Thank you.
Any more questions? Okay. Thank you. Thank you. Let's see. Where's your microphone? It's the second button, which is for this. And don't press the last button.
Okay. To go back, the upper one.
Yeah, go to the top button. We'll bring it down.
Okay, great. So thank you. Hello, everyone. I'm Damien Specq from the Meteo France lab, and I work in the subseasonal and seasonal prediction research team. And in this team, one of our main missions is to design a seasonal forecasting system based on the Meteo France coupled climate model. And for this, we make a lot of use of ocean analysis and reanalysis data in collaboration with our Mercator colleagues that I would like to thank here for their continuous support and for inviting me today. So with a few elements of context to start. So as I said, we produce seasonal, but also sub-seasonal forecasts, although I'm not going to talk about it in this talk, with the coupled climate model, which is called CNRMCM. So you have a representation of the model here on the left. I'm going to describe it afterwards. And basically making seasonal forecasts. So we've had an excellent introduction with the previous talk because it shares a lot of similarities with decadal prediction. So making a forecast with this model is basically making a climate run on the duration that you want, but also providing the model with realistic initial conditions in real time. And that's going to be the main point of this talk. And you have to generate an ensemble of forecasts in order to sample the climate distribution on the period that you're targeting, that you're forecasting. So there's a quick schematic illustration of the various forecasting ranges. So from short range weather forecasting, sub-seasonal forecasting, and on the right, seasonal forecasting. So basically we have forecast length of 7 months. And the main target in seasonal forecasting is the climate condition for the next trimester. So month 2 to month 4, average conditions after initialization. And these forecasts are issued once a month. So once a month, we update the forecast with a new one. And what do we do of these seasonal forecasts? So first of all, we are data providers to another Copernicus service, the Climate Change Service, C3S. Obviously, we're a research team, so we have to do assessment, verification, scientific studies with our own system. And more close to operations, we're collaborating with another team at Meteo France on the climate services side, which does a lot of thing about seasonal forecasting in interaction with users, but including in their activities, issuing a seasonal forecast bulletin every month, which I'm going to show a little bit afterwards. And finally, I end with this introduction with a quick reminder of why the ocean matters, but we've also seen that as well in the previous presentation by Dario. So as you know, the atmosphere has a chaotic behavior. It forgets very quickly its initial conditions. So making forecasts at such long ranges is possible thanks to other components of the climate system acting as slowly varying boundary conditions. And the first of which is the ocean. So a lot of predictability coming from coupled modes of variability between the atmosphere and the ocean. You've all heard about El Nino Southern Oscillation. There's also the Indian Ocean Dipole. Climate conditions over the mid-latitudes of our Europe, for instance, can be influenced by Atlantic SST anomalies and so on. So we have a great role of the ocean in seasonal forecasting. So basically, this is the outline with a very short illustration of downstream use of ocean reanalysis in the seasonal forecasting bulletins, and then the big part with seasonal forecast initialization. So in seasonal forecast bulletins, the question we want to, the question for which we need ocean analysis and reanalysis is what is the current state of the ocean? So those are graphical products that are provided by our Mercator colleagues and that we use to characterize this. So the current state of the ocean comes from a Mercator real-time analysis. So if you want the code, it's there, Sci4V3R1. And because in seasonal forecasting, we'll always work in terms of anomalies related to a reference climate. The reference comes from the average of the ocean reanalysis. So this is the glorious 12V1 Mercator reanalysis between 1993 and 2016. So as an illustration here on the left, you have SST anomalies for August 2023. So for one of our last real-time bulletins, you can see the positive SST anomalies over the Pacific related to the growing El Nino. And you can also see strong positive anomalies over the Atlantic, which have made a lot of noise in the last months. It can also be visualized as time series over the last year for some oceanic indices over specific boxes. So on the top, for instance, Nino 3.4 time series, where you can see the transition from the long-lasting La Nina to the current growing El Nino. So that's an illustration. So that's all for the downstream use of ocean reanalysis. Another big part, upstream use of ocean reanalysis for seasonal forecast initialization. So this is an illustration of our operational seasonal forecasting setup. We have a coupled climate model, CNR-MCM, which consists in 4 components. So we have an atmosphere model called Arpège. It is coupled to several land surface models embedded together. It is also coupled to a blue ocean model. So it's NEMO 3.6 at a 25 quarter of degree resolution and 75 vertical levels. And it's also coupled with in-house sea ice model called Gilles. So this is currently the 8th version of our seasonal forecasting system. Since July 2021, it's been in operation. And so it consists in producing real-time forecasts every month, as I said, with 51 members for each real-time forecast, and also providing reforecasts over a past period in between 1993 and 2018. So initialized the first of each month in the same fashion as the real-time forecasts. So those reforecasts enable to have the climatology of the forecasting system. They enable to calibrate the real-time forecasts and to make verification also of our forecasting system. And for all this, we need initial conditions for the ocean. So in real time, you need ocean analysis data as a starting point. And in the reforecast, you need ocean reanalysis data. So the problem is that it's a climate model. So it's been designed to make long climate trends, long climate projections are historical. We've also had a talk about CMIP like simulations. So it has no coupled data assimilation system. And therefore, we need to use on-shelf information that is already available to initialize our forecasts. So regarding the atmosphere and land surface, it's not the point of this talk, but we use ECMWF products gravitating around the ERA5 reanalysis, which also has a near real-time version called ERA5T. So it provides both atmospheric and land surface initial conditions. And then regarding the ocean and sea ice, so we have to rely on products from our Mercator colleagues. So the initial information for the blue ocean will come either from the glorious 12v1 reanalysis in the reforecast period or the real-time analysis in the real-time forecasts. So you have several variables, prognostic variables of the model that you have to initialize. And for our sea ice model, you also have a list of prognostic variables, and the model is multi-layer, as we've heard before about sea ice cube. So this requires specific prognostic variables to initialize it. And that's where the main issues arise, because ocean and sea ice data from the analysis or the reanalysis cannot be used directly. So obviously you have differences in terms of resolution. The reanalysis is at a higher resolution, but you also have differences in terms of the geometry of the ocean model that is used for the reanalysis versus our model in the seasonal forecasting system. And also differences in prognostic variables because, for instance, the sea ice model is not the same. So we had to find some workarounds for this with our Mercator colleagues. So this is a historical exercise, but basically the workaround is to use a preliminary simulation that is to say a continuous model run that will provide a consistent initial conditions for the coupled model. So that could be regarded as a poor person data assimilation. And for this, we have basically two options. A first one, which is the oldest one, is a forced and nudged oceanic run. So you make a run only with the ocean component, liquid and sea ice coupled together. And they receive forcing at the surface from atmospheric fluxes from ERA5. And in order to have realistic oceanic state, you nudge the liquid ocean towards the Mercator data, either reanalysis or analysis, in terms of temperature and salinity. And at the end, this run outputs the ocean and sea ice initial conditions. A second option is to use the full coupled climate model CNR-MCM, the same as is used for forecasting. And you nudge, so you relax both the atmosphere and the ocean towards reference data. So the atmosphere is relaxed towards ERA5 reanalysis, and the ocean is still relaxed towards the Mercator reanalysis data. And then this kind of RAN outputs initial conditions for all the components of the climate coupled model. So this is a summary of the initialization of ocean and sea ice. We have two options of preliminary simulations. And one advantage of this is that those simulations enable a smooth transition from the glorious 12v1 reanalysis in terms of nudging during the reforecast period, and then to the real-time analysis in the real-time period. So we have a first option, the ocean only run, which is a simpler, older approach that we still use today. A second option with the fully coupled nudged run, which is supposedly better for consistency because you also expect to have more consistent states initial states between the ocean and the atmosphere because it comes from the same model coupled together. But actually, it's not always the best thing for all components. For instance, we have noticed we have some issue with that. Is that option 2 with a coupled nudged run provides less realistic initial sea ice conditions. This is illustrated here on this figure. So this is a time series of sea ice thickness average over the Arctic over the full reforecast period. You have the reference data in purple above, so it comes from biomass. And then you have the time series for initial sea ice states with two options, option 1 in orange and option 2 in red. So both are underestimating the sea ice quantity. But option 2 is underestimating it by larger means. So as a result, in our current operational seasonal forecasting system, we actually use option 1 only for sea ice initialization. So we kept that one, and option 2 for initialization of all the other components. So blue ocean and the atmosphere, obviously, and the land surface. So this is my last slide, future plans and future needs. So we are currently preparing the next version of our seasonal forecasting system to be designed by next year. A very likely update in terms of modeling is the switch of ocean and sea ice to NEMO 4.2 plus sea ice cube. And regarding initialization, we may be tempted, it remains to be investigated, but we may be tempted to return to option 1. That is to say the forced and nudged ocean run due to the more realistic sea ice conditions. And regarding our Santa Claus list, we have the intention to extend our reforecast period up to 2022 for the next system. So far it goes only up to 2018. So we need to have the pre-processed reanalysis data up to that period. And we would also be interested, but we know that it's harder and it's the bottleneck. Actually, it's one of the main reasons for starting the reforecast in 1993. If we could go further back in time in terms of reforecast, for instance, that would be interesting to start in 1991, which is the first year of the new WMO climate normals period. So our reforecast would cover all that period. So I'm finished. Thank you for your attention.
Questions? Questions?
Thank you, Damien, for your nice talk. Did you have any sensitivity test related to the sea ice model, different model, or?
Honestly, I don't think so. What I'm introducing here, is the results of years of process, and I was not involved in all those previous developments necessarily, but I think that historically, so far the gelato in-house model was a key component of the CNRM-CM model. So I don't think there's been a lot of tests so far, but we are currently doing some with our plans to update to NEMO 4.2 plus sea ice cube. And so we are currently starting to set up the experiments of seasonal forecasting with this new ocean and sea ice model.
Okay, thank you.
Yes, there are online questions from Drew Peterson from Environment Canada. And he's asking about the options for initialization. Do you have a did you do a direct test of initialization shock in option 1? And how do you diagnose a shock actually?
Okay.
It is hard to diagnose, that's what he says.
I'm sorry, it goes a bit like further my knowledge of the historical development of the system, but yes, there is an initialization shock, and it was actually part of some work to investigate how the coupled nudged preliminary simulation would help reduce that shock. What I did remember about those work actually was that it did not improve seasonal forecast skill. So, but I can't tell more so far.
Okay, thank
Sorry.
you. And he also asks about the source of perturbations and what components are there in.
Yes, so you mean the generation of the ensembles, I guess.
Yeah, I guess.
Yes, it is a perturbation of only of the atmosphere. So it's the dynamics of the model that is perturbed all along the integration of the atmosphere model by adding small perturbations that were also defined actually in a preliminary run where the model was continuously integrated and nudged towards a reference towards ERA 5. And then the errors made by the model in this run were saved, and they are used as perturbations in line when the model is running.
Okay, that's very precise. Thank you. Are there any more questions in the audience? Or?
I have a question, sorry.
Yes.
It's related to the ensemble generation. When you have 51 ensemble members, but you only use the one reanalysis as the initial conditions.
Yes.
Yes. Do you think it's possible to, I mean, this is 1/12 degree reanalysis. It's possible to use the 1/4 degree ensemble reanalysis as the initial conditions?
It could be. Actually, I don't know whether this option had been considered before. But yes, you mean it could, like having an ensemble reanalysis could indeed like add another source of perturbation. Actually, what I have to confess, but I didn't mention in the talk, is that there is already some kind of oceanic perturbation in our initialization, because we are not initializing straight on the first of each month all the members. We actually do some lagged initialization. We have 3 batches of members, so they are starting with slightly different initial conditions, both for the atmosphere and the ocean. So you have some ocean perturbation in that way. So I think that was the option that was retained at that time, but that could definitely be considered, like using ensemble reanalysis to increase or to develop the perturbations a different way.
Okay, thank you. Shall we the round table? Shall we do?
Yeah,
yeah.
I think. Yeah. What do you think?
Thank you so much.
Thank you. Thank you, all speakers, and so
the round table will be the speakers. We can put the chairs here.
Yeah, if the speakers want to join us at the table for the round table, and we can try to. Okay. So there are. Okay, so this time we do a real round table, facing the camera and everything. Okay. So.
Yeah, we're missing one.
We are missing one speaker. Dario. Dario is sitting there, and Daniel. You want to? Okay. So this time we move everything. Actually, you can see.
Yeah.
Yeah. So now that we are here, who wants to start? well.
Okay, actually, go ahead. So here's a question for Lee. So I think one of the recommendations coming out of this meeting is intercomparison project or projects. And Lee is telling us that the way we get reanalysis into the CMIP process is to actually get those reanalyses in the right form so that the users can immediately download and do comparisons and all kinds of studies like that. So would it be a reasonable idea to have as one of the outcomes of the reanalysis project some recommendations or actually creation of data sets that could go on the IPCC websites along with uncertainties based on this intercomparison project?
I mean, if I may, yeah, I think that would actually be, it would be a bit of a win-win for everybody, because if you, I don't know the precise details of how reanalysis files look, but I imagine you're not all using the exact same details in every file. So by forcing yourself to use the CMIP like standardization, make it compliant with CMIP, you'd actually make your own intercomparison a lot more straightforward as well, because you'd be able to access the tools that we have. But also, if everything was labeled the same and you had the same metadata in all your files and you had the same directory structures and you had it, just if you want to do an intercomparison project, you need everything to be standardized. And standards exist already. You wouldn't have to reinvent the wheel.
Let's say I'm not sure it's feasible right away, but maybe with 1 degree monthly could be feasible. Yes, Chun Chui. Yeah.
I know also now they have summarization tools, so we can take advantage of it. Just change the metadata. I think it's not a big, I don't think it's a big effort of work. But I do have a question. You mentioned ops warming, but I'm not too sure that currently this project is still running on, or is we stopped? Do you have any plan? What's the status of this ops?
Yeah, I don't know much about the actual project, rather than I've accessed I use the data that's in that format. So in general, when, for instance, the World Ocean Atlas data that we use for things like temperature and salinity and nutrients, as part of, in the early days of ESMVL tool, we developed a tool to convert World Ocean Atlas data to OBSUMIT format. I don't know about the formal project structure, though. I suspect you're right, that it doesn't actually exist very much anymore.
I have a question. I will obviously we will dig down to see how, because the data, you're going to use the OBSUMIT, the older version. That's the data we found that is new older version. That's what we want to see how to integrate the new version of the data for you to use. The second question is related to, you mentioned the resolution is in there. Okay, maybe now. Sorry. Yes, it's my fault. The other questions relate to the resolution. You mentioned the CMIP 5. Even I think CMIP 5, yes, maybe a lot of data is 1 degree, but they do have high-res map. It's 1/4 degree, but even more. I think UK Met Office, I can find the rechart. They even have 1/12 data resolution map. I think the specific case they have very high resolution. I think my impression that also CMIP is going to high resolution. I mean, I don't know the plan for the CMIP 7, but it's every community goes to the high resolution. So I think my question is that I'm not really agree with your point that the high resolution is not needed from the if we compare reanalysis with the model data, because CMIP is low resolution and reanalysis is high resolution. If you find a disagreement, is what's your opinion about this one?
Okay, so in CMIP 6, there is high-res MIP, which is a very specific project to look at high-resolution But one of the conflicts that is occurring within the CMIP6 is that it's very difficult for high resolution models to complete the deck. You know, the simulations, they require several hundred years of data production, and it becomes very expensive. So I know that for CMIP7, which is still in the planning phase, but they are talking about having a separate high-res deck. So the entry to that experiment is a lot lower. And that would mean that they wouldn't have to run from 1850. They could run from 1970, for instance. So in the future, it's still, like I said, it's still in the planning stage, but it is likely that there will be more higher resolution models in that specific domain. However, in my experience in CMIP6, most of the models that I have worked with in the current generation are about 1 degree. And I mean, there is variation across the board, and there's all sorts of different grids. And some modeling centers have more budget to produce like fancier models. So it's, you know, there's not a one answer for everything.
Thank you. Okay, so we have also a Slido that we can look at to look at the results to see what were the feedback from the audience. But also, so we talked about having the data under the right format so that they can be useful for the CMIP community, but there is also having ensembles of reanalyses that would be very useful for the decadal and seasonal prediction communities. So that's also a point that we can note, that also the period going further back in time is important, and with ensembles.
If I may, I'd like to share my favorite piece of news from CMIP7. It's so as we saw in the past, we've seen this RCP 8.5 and SSP 8.5. So the first part of the number represents the socioeconomic scenario, and the second represents the radiative forcing at the year 2100. So SSP 8.5 means that they're expecting in the scenario 8.5 watts per square meter of additional warming. So that's a measure of the greenhouse effect. But the good news is that in CMIP 7, the highest radiative forcing is expected to be 7 watts per square meter. So 8.5 is going to be excluded. So the worst case scenario got less worse. I'm really just so excited about that. It's just such a wonderful piece of news. Sorry, I had to say that.
I want just to add that, in fact, in the decadal prediction project, the scenario for the start dates after 2014 is the SSP2, which corresponds to RCP 4.5. So I think that also in CMIP, they are already thinking about it.
The seasonal scale at the moment is okay. So do we display the Slido results? Okay. So what are the interests of the climate community in ocean reanalysis products? Climate process studies is coming first. So you did not, well, you talked about the statistical validation in a way. You also, but you mentioned in the seasonal forecasting talk that you were using also the reanalysis to understand in the Nino the processes or the ocean states. So that's more, I think, what is mentioned here. So in the knowledge of our people answering this Slido, the climate process studies comes first, and then the calibration, initialization, and validation. Okay, boundary conditions to other 4%. What is other? So that it's changing in real time. People are adjusting. Okay. And you want to do any comment on that?
Current 23.
23.
Top right.
So I guess it's all the time like something like 10% of the audience, total audience. So maybe we have 200 people online. Is that a correct guess? 140. So they left because they know the talks are ended.
I think we have another one question. If not these options, what they would like to have? Huh.
If other. Okay, this was if other, could you specify? They use a reanalysis product to assimilate these products. Okay. Some are nudging or assimilating reanalysis products. Maybe. Don't know about that.
I think that at least for our seasonal forecasting initialization, I think that like relates to the initialization problem.
Yeah, probably. Yeah, maybe that's a confusion with this.
Yes.
More initialization than data assimilation. Yeah. Okay. What are the mandatory requirements to ensure your use of reanalysis data? The mandatory requirements: accuracy, reliability, consistency, uncertainties, confidence, that it is freely available on a server that is functional. I mean, that will fulfill huge requests in a reasonable time with no password and nothing to ask me.
No JavaScript.
No JavaScript, okay. I also prefer products that are well documented. ERA or CAMS C3S could provide good examples with different levels of details and useful summaries. Good. A laptop with clear knowledge and idea on quantitative data. Methodology of data collection, accuracy, period of data collection. Okay. The curation of data. So all sorts of things. Regular availability, validate data, daily data. Okay. Okay, I think these are quite in line with the usual requirements we get. And so this will all be collected and summarized and put together in the report after this workshop. Okay. So thank you very much for your feedback, online people. Do you want to?
That's it.
That's it?
If we can have, I have a question for discussion, which I know if you want to leave and call it a day, that's fine. But it's one of the things that we talk about a lot in CMIP's like community is like how can we have a positive impact on like climate change policy? Like surely we don't want to spend the rest of our careers just watching the ocean die. Like how can we, you know, try to make it better in the future? And I don't know, is that something that the reanalysis community thinks about? Like I've noticed that today is very focused on science and very less focused on feeding back to decision makers and policymakers. So what happens?
So we've been doing a lot of efforts in that sense with the Ocean State Report, which is our contribution at the moment, and Karina is working hard on that question. And we are also doing a summary for policymakers, but of course we are still doing a lot of efforts to try to understand how to connect with the society and really give them useful information in the format they require, etc., etc. So I think all this community is really aware. For instance, we are trying to provide useful information for the state of, let's say, the quality of the water, so the changes occurring in the marine environment in the European seas, etc. So all sorts of impacts, marine heat waves and stuff like that. Of course, the reanalysis is for the past periods and the present. So we are analyzing the current state and the recent changes. And so that's all that we can provide as a community for. I don't know if someone wants to add something.
Yeah.
Well, I think that
Maybe you can complement on the machine cost or I don't know, because there was a question on
the machine on the
limiting
resources for
limiting computing resources so that we do not spend too much carbon on computing. And this is a tricky question, but
yeah, it's not really something monitored today when we produce a new analysis and so on, but for sure it's something really important, and if we have to communicate on that, that's something that we have to also homogenize in terms of the way to compute this carbon footprint when we compute a new analysis. That's something that could be really important also for the community. But it's not so easy, and we don't have exactly the same way to compute this kind of carbon footprint in each computing center, for example. So as a user of the computing resources, it's not easy today to have a clear information about that. But regarding the monitoring and so on, there is more and more information about what we can monitor with the analysis and combining with real-time information. And for sure, that's something done for policymakers and for citizens and so on. So that's really one priority for, at least in Copernicus Marine, but for sure in all the community.
And that's also, I think, the question of the variables that we could, let's say, produce that are not observed, but which could be emulated or maybe modeled using reanalyses and many techniques we start doing, but we have very limited capacity to validate these variables, but that would be interesting information that only we can provide. And what would be the priorities in that sense? What do you need to validate that you don't have observations for? And we could provide from a modeling point of view, but with uncertainty, with some uncertainty.
Yeah, I just wanted to add a small thing, I guess, but there's one lever that we have, which is kids, education, basically. So if we make our ocean analysis so easy to use and so kind of transparent that a teacher can use it in like to a 10-year-old, I think that's one place we can have an impact in terms of the future.
Also, just want to add what the climate policy. I think because in the catalog in the Marine Service catalog data, in the future there will be a summary of each data set. I think that one can help because that address the not only the quality but also tell users the information you can take from this data set. Definitely, we are only talking about the ocean reanalysis particular, but in the Marine Service, they have different types of data set and forecast, for example, satellite data set. Yeah, so we are only part of it. That's why, yeah.
Just to add something about the digital twin concept, it is also it's not really precise today what will be included in these concepts, and for sure it will be not the same in for all the type of digital twins. But at our level, for the moment, the objective to build this new concept is really to provide new information for the users, including we are users, potential users of this type of technology, to compute our own new indicator or metric based on a large diversity of products that will be available on this type of infrastructure. So that's really also something that could be built to produce new type of information for decision makers, but also for the developers of model or developers of producers of reanalysis and so on.
Yeah, I think the interactions with the public are very important as well, I think. And I'm not sure that the ocean community necessarily does a lot of it, but for instance, last week in the news, you probably saw the temperature spike for September 2023. But that was Zeke Hosfather's tweet, the shockingly bananas comment that he made. That was based on the reanalysis, wasn't it? Because wasn't it? No, it wasn't. No, but it was, the front cover of several newspapers. And, that was data that I'm sure that a similar response would be seen by the public in the ocean as well. people do care about these things.
Yeah, I think we need to close. Even if this discussion is really interesting. It was a very interesting day again. You want to say finally?
No. Thank you all very much, and thanks so much to the speakers. See you guys tomorrow morning. What time is?
Tomorrow morning, starting at 9. Starting at 9 tomorrow morning with presentations from the atmosphere reanalysis community. Thank you very much.
Thank you very much.
We didn't make any plan for this evening, but I'm sure you can meet some of you. I can't tonight. I have to go back to my family.